Two, ooh, ooh, 1, 2, 1, 2, 1, 2. Astronomical wall. Yeah, astronomical wall. Comic Conic. Welcome 1.61. 1.61, 1.61, 1 2 3 4 5 6 7 8 9 10. 1 2 3 4 5 6 7 8 9 10. 1 2 3 4 5 6 7 8 9 10. 1 2 3 4 5 6 7 8 9 10. Top two, because we are talking about bits. Oh, 1 2 3 4 5 6 7 8 9 10. Hey.
Yeah. So this is the pointer, right?
Yes, that's the pointer.
And that's for going forward, and that's for going backward,
Yes.
right? So it was the same as in the other hole.
1, 2, 3, 4, 5, 6. 2, 2, 2, 1, 2, 1, 2, 1, 2. Can you hear something? 2, 1, 2, sharp, sharp. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 10, 10. What? Yeah, lang. Ouija. No, this one. No, this one. Yeah, the zero, yeah. Yeah, but sounds loud though. Let's say turn it down.
let me just say one thing to the speakers. The time that you will see on the monitor for Division H sessions, it's the time that you have for your talk. So it does not include the question time, okay? So that you will see the time flashing when it's about to elapse. And that's just the time for your talk. Question time will be organized by the chairman, okay? Okay, welcome everyone. Just a reminder, if you are here sitting in this room, it means that you are interested in participating to Division H meetings. Division H is Interstellar Medium and Local Universe. And this morning session will be on metals and feedback in local galaxies. And our opening and will be by our president, Monica Rubio. So I'll give the floor to her.
Thank you very much, Edvija, for the introduction, and I welcome all the participants to this Division H meeting this morning. And I would like to mention that thank the steering committee of Division H for all their helpful and very commitment work during the 3 years that they have served on the committee. We have had the task to select and propose PhD winners, PhD prize winners to the executive committee from all the abstracts received. And also we assess all the proposal for symposium and focus meeting during the 3 years. So most of the symposium and focus meeting in this General Assembly, and also we had a double work on this period. On 2022 was done by the steering committee. I would like also to share with you that this division has 3 commissions, one which is specifically on the local universe that had been chaired by Gracina Tautzvaisien, the Commission H2 Astrochemistry, chaired by Paola Caselli, Commission H3 Planetary Nebula, President Orsola De Marco, and Commission H4 Stellar Cluster through Cosmic Space and Time, who chair is Francisca D'Antona. So several of the members of this division steering committee have finished their term. I myself, I'm finishing. Our vice president, Klaus Leiterer, will replace me since next Friday. And Edvige Corvelli that will be the vice president of this division. And I would like especially to thank both of them because they had been instrumental and very helpful in the organization and the activities that the divisions has had during the 3 years. So just a little bit of information of what the steering committee and the division task and work to do. And as I mentioned, well, first of all, welcome for all of you who are here in person as well as those who are online. And as I told you, one of our decisions, or one of the things that we have to do, is to select the PhD prize winners. And those who are selected and awarded the IAU PhD prize have we have decided to have them with an invited talk at the division day, and also IIU grants or gives them a certificate. So it is my pleasure to call Piyush Sharda on stage. And he will give us a talk. Sorry, he will give us a talk on his PhD work, which was the role of metal from molecular clouds to galactic disk. So,
Thank you. Thank you so much for this really amazing honor. And thank you so much for having me here to tell you a bit about my PhD work that I did at Australian National University with Mark Krumholz. So we are in Division H, local and interested. Oh. So we are in Division H, local ISM and the local universe. So I thought it would be really cool to start with Cosmic Dawn. And talk a little bit about what's really happening in the very, very high redshift universe, and why is that? Why can you not do this research without really understanding our ISM in the Milky Way, as well as nearby galaxies, as well as the local group? So we have seen this image a lot of times over the last couple of years or so. Beautiful image, very, very high redshift galaxies. We are now approaching an era where first galaxies are visible, we can see them, and James Webb has a lot of observations of these galaxies, and there have been lots of talks throughout this General Assembly as well on these. So to summarize, these are some of the key points or key things that all of the James Webb data we have on the first galaxies are telling us. These galaxies supposedly have really compact sizes, like few tens of parsecs, sometimes like 100 parsecs at most. It's also a question whether you can actually call it a galaxy at that scales. These are really, really dense. So surface densities are really, really high, up to 10,000 times the Milky Way surface densities. They have extreme radiation fields, but they have normal star formation rates. So star formation rates are something like an order of magnitude solar mass per year, and so on. They seem to have little dust in them. They have low metallicities, between 0 to 1% solar, often even 10% solar. And they potentially also harbor massive black holes, because we see some signatures of AGN in these galaxies as well. Now, all of these points have big question marks on them, so take them with a pinch of salt. But this is what we currently understand about these galaxies. My PhD has been focused on understanding how these galaxies are built, how they're assembled, and how they evolve over time. But doing so is not possible without a multi-scale approach. And the reason for that is these galaxies are so tiny. Like, imagine if you have an entire galaxy of a size of a few tens of parsecs. A single massive star can yield dominant signatures in the spectra of these galaxies. So understanding what is really happening at AU parsec scales in the ISM of these galaxies is really, really crucial. So I'll divide this talk in two parts. One where I focus on parsec scales, or lower, where I'll talk a bit about low metallicity star formation, population 3 star formation, and so on, because these were the ISMs that were the building blocks of these first galaxies. And on kiloparsec scales, I'll talk a little bit about metal dynamics and distribution, and what can we learn from the local universe, as well as at low redshifts, to then apply to these galaxies in the future. So let's move to the first part. We normally think of star formation as molecular clouds collapsing, 10 Kelvin gas forming stars. However, this picture deviates a lot when you go to lower and lower metallicities. So if you do a thought experiment, let's say, where you pick a molecular cloud, you make it collapse, so the density is increasing on the x-axis plotted here, and you see what is the response of the gas temperature to this increase in density at different metallicities. And the reason we care about densities and temperatures is because that sort of gives us the Jeans mass or the fundamental mass that we care about when we talk about the mass of stars that will form in a given molecular cloud or in a given ISM. And you can see from this plot that as you go from solar, so 0 over here is solar, to 1/10 solar and so on, all the way to POP3 stars, so no metals, the temperature that the molecular cloud attains as a function of density is vastly different, which means the genes masses you get are really, really different. And the sort of star formation that happens and then feedback and so on are also going to be really, really different at these low metallicities. And it is this low metallicity regime that has not been explored as much because of lack of observations. I mean, the more you go lower in metallicity, the more it becomes completely a theoretical construct. We haven't observed any POP3 stars, for example, as of yet. One thing that becomes really important is the chemistry. So ISM chemistry, you cannot get by without understanding ISM chemistry if you want to understand low metallicity star formation, because your gas is not at 10 kelvins anymore. So we understood a bit about the genes masses, so we can already expect that because the temperatures are different, the genes masses are going to be different, and that potentially has some significance for the initial mass function of the IMF in these galaxies. So let's create a scale in metallicity where we go from 0 all the way to supersolar metallicities. Now, what do we know about the IMF at all of these metallicities? We know the IMF in the solar neighborhood, it looks like this, has a very characteristic peak mass, which is less than solar. So we call it a bottom heavy IMF. It's very well understood, and well, it's not understood, but it's very well, nobody debates this is the IMF in the solar neighborhood anymore, other than some people. And all we know about the first stars or POP3 stars, all we can agree on is that the IMF was top heavy. So the characteristic mass or the peak mass of the IMF should be more than a solar mass. But what exactly is the IMF? We still do not know. And because we haven't observed any of these stars, we have to rely on simulations or theory. But none of our simulations and theory include all the relevant ISM physics. So we have no idea what the IMF is like. All we can agree on is that it is top heavy. So if you take just these 2 points, zero metallicity and solar metallicity, you see the IMF was top heavy here. It was bottom heavy here. So as astronomers, we love to fit straight lines to 2 points. So let's say that the IMF has evolved from being top heavy to being bottom heavy as a function of metallicity. That's all we can sort of say at the moment. But there are lots of systems in between. We have metal poor stars, we have first galaxies, ultra compact dwarf galaxies, globular clusters, LMC, SMC, also massive elliptical galaxies. So there is some reasoning that okay, they might have different IMFs, different environments, different sort of gas properties, but we don't really know what exactly is happening. There's lots of evidence, some strong, some weak, but we can't say much more for certain at the moment. But we can try and answer this question. Can we say something about when we expected the IMF to become bottom heavy as a function of metallicity? And again, the clue lies in the chemistry of the interstellar gas. So it turns out that if you solve for the chemistry of the ISM as a function of metallicity, you achieve some distinct chemical regimes in this particular space. So what this plot shows is the relative importance of heating things that can heat the gas versus things that can cool the gas. I have masked out the heating processes because we care about cooling at the moment for our genes, for genes masses and temperatures. And you notice that at low metallicities, we have cooling that is dominated by molecular hydrogen. We don't have enough metals or dust. There is an intermediate regime where metal line cooling can become dominant. And then at solar metallicities, dust really governs gas thermodynamics quite a lot. This picture can change a little bit, fluctuate a little bit based on different properties, other properties as well, like density and pressure and turbulence and so on. But this picture already tells us that because of these distinct regimes in chemistry, we'll have distinct temperature regimes, and then that would give us some distinct characteristic masses or IMFs. If you plug all of this into some models, you can then start to look at the variation of the peak mass of the IMF as a function of metallicity for, let's say, 2 different gas densities or ISM pressure environments. And as you expect, it seems to be very top heavy at very low metallicities and sort of starts to evolve down to bottom heavy at high metallicities. And then basically everything sort of converges to something like 0.2, 0.3 solar masses at 0 metallicity. This is something what we see in the Milky Way. In high pressure ISMs, the picture is similar qualitatively, but quantitatively a little bit different. Now, the reason for doing all of this modeling is that we can actually learn something about the simulations that we would like to do to really understand what's happening in a 3D sense. So these models become a pathway to developing simulations. And that has been the main goal of the Popsicle project, where we are trying to simulate population 2, population 3 star formation environments, ISMs, including all the relevant physics as well as chemistry. So now we do this with a well-known code called Flash, grid-based code, where we follow the collapse of molecular clouds at different metallicities up to 12 to 14 orders of magnitude. So we start from densities of, let's say, 10 per centimeter cube, go all the way to 10 to the power 15 per centimeter cube to really understand what's happening at AU scales. How are these stars forming? What's the interaction between the stars and the accretion disk? What are the masses of these stars? And how is chemistry, radiation feedback, magnetic fields, and turbulence impacting this entire picture? Of course, the expensive part is resolution, as is the case for all simulations. The non-trivial part is how do you couple chemistry on the fly with radiation? So if you like to know more about this, please ask me a follow-up question. Right. So as you go to lower and lower metallicities, it turns out that you need to do a lot more simulations than you would have to at solar metallicity. And that's because turbulence and fragmentation become really, really stochastic. And if you simulate the same box, same identical initial conditions, again, changing just the random seed, we have a lot of random seeds in all sorts of hydro simulations, you might get completely different results on the number of stars you're forming. So you need a lot of statistics. And this is something that all the groups working at low metallicity star formation are now sort of converging on and agreeing, which means we need a lot more time on HPCs than we initially thought so. This plot shows that, so for example, all the columns here have exactly the same initial conditions, just changing the random seed. And then sometimes you get just one POP3 star, sometimes 5, sometimes even 10, 12, 14, or so on. There's a lot of variations here. But one advantage of doing a lot of these simulations is that we can gather statistics on some key properties like the mass of the stars and start to construct an IMF from these simulations from first principles. We are not there yet. So this is a lot of work in progress. I've just made a cartoon figure to sort of show what are we actually looking at in terms of the IMF at population 3 versus at population 1. So POP1 IMF, there are lots and lots of studies on what sets the IMF, how radiation feedback, magnetic fields, turbulence sort of interplay to give rise to the sort of IMF we see in the solar neighborhood. For POP3, the situation looks quite different at the moment. So the physical processes remain the same, but their role can change quite a lot depending on what exactly is happening at the AU parsec scales and how these stars are gaining mass and how the feedback is impacting their mass growth and so on. So all we can say right now is that we knew that different physics will set different parts of the IMF. We know that very well. But the role of these different physical processes can also change a lot at different metallicities. And that's what we are like sort of driving towards, creating an IMF for population 3, population 2 conditions from these simulations. So look out for some papers in the next year or so on this. Some key caveats are, of course, these simulations are very computationally expensive. They take half an year to run. So if you make a mistake, half an year of work is gone. And they also, we'd again like to go to even higher resolution. Right now we have AU scale resolutions, but we'd like to go to sub-AU because some processes that we really care about, you can only really resolve them at these resolutions. The future here, in my opinion, now is GPU accelerated computing because we have sort of reached some limits with our CPU based codes. So we are also working on a new code called Quokka, where we can get a lot of speed advancement in the sort of time we need to do the simulation. So what we could do on Flash in 48 hours with 400 cores, we can basically do the same with one GPU in 12 hours. So we can go much farther in resolution. We can do it much faster and much better. And as HPCs around the world also turn to more and more GPU-based computing, this will be the future even in astronomy in terms of simulations. All right, so this is all catering to AU to parsec scales, but I showed you some things about first galaxies in the beginning. And the reason is that the observables we have from James Webb are these sort of spectra, emission lines, and so on. they are on much larger scales than AU to parsec scales. So to actually then be able to compare with observations after you're doing all of this small scale ISM physics and chemistry, you also need to say something about what's happening on larger scales. And that's where we can learn a lot from the local universe. Just skip this slide. So this is a local galaxy. We understand these galaxies have H2 regions. Oh, wow. And we can now sort of look at these metallicity maps and understand what is the metal distribution in our local galaxies. We have done this for thousands of galaxies now, thanks to IFUs and so on. And we are also starting to explore this at higher redshifts now. I mean, there are more caveats at higher redshifts when you do this sort of analysis, but it's becoming possible. So we want to be able to model these galaxies and the chemical evolution in these galaxies to then ultimately be able to say something about the first galaxies. And we have been doing a lot of work, we as in the whole community. So right from the 1970s to now, there's been lots of models that look at how can you explain chemical evolution in galaxies, including the role of inflows and outflows and so on. But something new that we have been working on is understanding ISM dynamics on kiloparsec scales and how that impacts metallicity dynamics and metallicity distribution in galaxies, particularly in the local universe. So these new models, in addition to the typical solving for mass conservation, metal conservation, also solve for energy conservation. So you can start to say something about the resolved gradients and distribution of metals in galaxies. And they also include something which we call the differential enrichment of outflows. So I'll come back to that in a minute. Actually, I'm a little bit out of time. I will maybe skip to some of the key plots. So in this plot, basically what these models predict is as a function of the galaxy's stellar mass, what are galactic winds doing to the metal distribution in galaxies, in local galaxies in particular. And you can see there is a lot of, the models are basically quite unconstrained because we don't have a lot of observations of galactic winds in particular. The 5 or 6 triangles you see are the only observations where we can actually understand the metallicity of the wind as compared to the metallicity of the ISM. So we do really need a lot more observations in this space. Of course, they're really, really challenging, but they do show a trend in the sense that as you go to lower and lower masses, the metallicities of the wind seem to be much, much higher than the metallicities of the ISM. And that has some important consequences for the mass metallicity relation, which was already said like 10, 15 years ago, but also for resolved metallicities in these galaxies. And these are the sort of masses we look at when we talk about the first galaxies, by the way. You can also do more things like comparing resolved metallicity gradients with kinematics of the gas, because we have a prescription for ISM dynamics and energy in the ISM. And we can start to look at, okay, as a function of V over sigma, which sort of describes the rotational support of a galaxy, what is the metallicity distribution looking like? So some things we see which are very expected, that at high velocity dispersions, we have a lot of efficient metal mixing, so we get flat distributions and so on. Then you can take this and you can actually compare this to TNG simulations as well, or any other hydrocosmological simulations. And you see that models and simulations sort of roughly agree on where galaxies should lie in these sort of parameter spaces. But these are relatively new parameter spaces. We are going beyond the typical mass metallicity stuff. We are also starting to look at kinematics of the gas, which is a new frontier and which we need a lot of work on in the future to understand metal dynamics and distribution. All right, so I'm already out of time, so I'll just summarize here that to understand the first galaxies, we need to know our low metallicity ISMs, but we also need to understand metal distributions on larger scales. And then combining the two, we can then say something about the first galaxies, and in turn learn a lot about our own local universe in the ISM. Thank you.
Thank you. Thank you very much for your talk across the whole universe at this point. And let me see if there are any questions. I see just one here.
Very nice talk. My comment is, or question is, you include ram pressure and photoionization in your models. And the reason I ask that question is that locally, within a few parsecs of the sun, helium is more highly ionized than hydrogen. Sounds weird, doesn't it? How come?
When you talk about models, do you mean the simulations and the low metallicities? Right. So the question is, why do we see helium being more ionized than hydrogen? Okay. Yeah, I'm not sure I know the answer to that, to be honest. What we see, at least in the low metallicity universe, is that unless you have a very massive star with very extreme ionizing field around it, helium is not as highly ionized in general. Yeah. So I'm not sure what would cause that. Is it cosmic rays? Right. Thanks.
Okay, we have time for another question. Yes.
Thank you very much for your talks, very interesting. I have a question about the metallicity gradients. So as far as I know, they're usually determined from H2 regions. And I was wondering if you know of a metallicity gradient or lack of for example, more neutral, warm neutral mediums.
Yeah, I think the most metallicity measurements that I'm aware of, or that I've looked at to do these models, come from H2 regions. So we're looking at ionized gas, in particular. I'm not an expert in the literature or when it comes to warm neutral medium and what the metallicity gradients there could be. Sorry, yeah.
Okay, no problem. Thank you.
Okay, we can move to next speaker. Thank you very much again. Michael Romano will talk us about the imprint of star formation-driven outflows on the evolution of dwarf galaxies.
Thank you so much. So, hi everyone. My name is Michael Romano and I'm a postdoc at the National Center for Nuclear Research in Warsaw. So today I will tell you about some recent results we obtained on the effect of galactic outflows on the evolution of local dwarf galaxies. And here you can see some of the main collaborators of this work. So let me give just a brief introduction on this topic, as it was already been touched a bit in the previous talk. So here you can see a composite image of MET2. Here the blue emission is the stellar emission, and in red you can see the H-alpha emission coming out perpendicularly from the stellar disk in this huge outflow of ionized gas. However, if you want to describe the evolution of this galaxy as a function of time, we have to consider the so-called baryon cycle. That is the set of complex phenomena ruling the interplay between the gas, dust, and star formation within the galaxy. And in a very simplistic way, we can say that at the beginning of this cycle, the gas in the galaxy can cool down to allow the formation of new stars, which in turn evolve, giving rise to stellar winds and supernovae, and then reaching the ISM with metals and dust. And both star formation and the AGNs can exert a feedback in the host galaxy that can be eventually responsible to stop the formation of new stars by pushing the interstellar medium material outside of the galaxy. And you can see that depending on the outflow velocity, this material can stay bound to the galactic disk or brought just outside into the CGM, where it can still be reused for future star formation. But in the most extreme cases, it can also leave completely the galaxy reaching the intergalactic medium. And so because of their importance in the baryon cycle during this talk, I will specifically focus on feedback from galactic outflows and specifically on feedback driven by star formation. So feedback is usually invoked by all cosmological simulations and chemical evolution models in order to reproduce the observations of local and high Z galaxies. And a way for showing the need for feedback is by studying diagnostic diagrams based on observational properties of galaxies. So for instance, here you can see the so-called dust formation rate diagram that shows the specific mass of dust as a function of specific star formation rate, in this case for local dwarf and high Z galaxies. And this can be seen as an evolutionary diagram in which the galaxies at the beginning form dust grains at very high specific star formation rate or young ages. And after some time, this dust can be removed or destroyed from the interstellar medium due to star formation or outflows. And the solid lines here represent different tracks from chemical evolution models attempting to reproduce the dust cycle in these galaxies. And you can see that these models depend on several input parameters like the initial mass of gas, the star formation history, the initial mass function, but also the presence of inflows and outflows. And in particular, the outflow efficiency is usually parameterized through this quantity here, eta, that is called mass loading factor, which is the ratio between the outflow rate and the star formation rate of the galaxy. So when this quantity is much greater than 1, it means that the outflow is much more efficient than the star formation in depleting the gas and the dust from the interstellar medium. And as you can see, these models are very dependent on the outflow efficiency. In particular, the models with the low mass loading factor, like the purple or gray lines, are too flat in order to reproduce these observational trends. And in particular, these models need very large outflow efficiencies in order to reproduce at least the observations of the older galaxies, spanning almost 2 orders of magnitude. So from this picture, it's clear that we really need some observational constraint on galactic feedback in order to provide a better description of the baryon cycle in these galaxies. And dwarf galaxies represent one of the best targets for this because they are much more sensitive to feedback with respect to higher mass galaxies. And also, they are thought to be analogs of high redshift sources because they share similar properties in terms of star formation efficiency, metallicity, and size. So they offer the chance to provide also some constraints on feedback also in their primordial counterparts. So because of this, we selected a sample of dwarf galaxies from the Dwarf Galaxy Survey. That is a collection of 48 low mass sources that have been observed in the far infrared with Herschel, and you can see them here at 70 micron emission. These galaxies are at distances smaller than 200 megaparsec. They are characterized by subsolar metallicities, and they lie along the main sequence of star-forming galaxies. So in order to identify outflow in these galaxies, we took advantage of the ionized carbon line at 158 micron that was observed with the PAC spectrograph on board of Herschel. And we choose this line because it is one of the strongest lines in the far infrared regime. It is a good tracer of atomic gas, but also it was already used to detect the galactic outflows both in the local and high redshift universe. And so we selected a subsample of 29 galaxies from the parent DGS sample in order for this target to be completely covered by the PAC's field of view and having a good signal to noise in situ emission. And we started searching for outflow signature in this galaxy by fitting the C2 spectra with a single and double Gaussian profile, with the latter including both a narrow and broad component, and also by inspecting the corresponding residuals. So in some cases, like the one shown here, the presence of the outflow was evidenced by the broad wings at high velocities of the spectrum that couldn't be reproduced with a single Gaussian profile. However, when fitting the spectrum with a double Gaussian function, the broad component was matching the high velocity wings, clearly improving the fit. And so in total, we found that 11 out of 29 galaxies were showing clear signature of outflowing gas, while for the rest of the galaxy, if the outflow was present, it was too faint to be individually detected. And from each of these spectra, we extracted different information. So for instance, from the narrow component, we measure the C2 luminosity and the corresponding star formation rate, while from the broad component, we measure the properties of the outflow, including the outflow mass, size, and radius, and velocity, sorry. And so we use this information to compute the outflow rate that we compare in this plot with the star formation rate of the galaxy. Here, the circles represent individual outflow detections, while the squares are just the results from some stacking on the sample. And everything is color-coded by the mass loading factor. So as you can see, our galaxies lie along the one-to-one relation in between the observed relation of local star-forming galaxies and AGNs, and suggesting that the mass loading factor is close to 1, which is much lower than what predicted by chemical evolution model. So for sure, we need to refine this model for a better understanding of the baryon cycle. And we also studied the CGM and IgM enrichment due to these outflows by computing the escape velocities of these galaxies that are defined as the velocities required by the gas and the dust in order to escape out of the dark matter potential of the galaxies. And we compare them here with the outflow velocity. So again, here the circles represent our individual outflow detections, while all the other markers are local starbursts or dwarf galaxies from the literature. And everything here is color-coded by the stellar mass. As you can see, again, our galaxies lie along or above the one-to-one relation, suggesting that their outflows could really bring the gas outside of the galaxy and reaching the CGM. And to quantify this, we also compute the escape fractions, which are defined as the fraction of the outflowing gas with velocity higher than the escape velocities. And we found that on average, 40% of this gas can actually escape into the IGM. It is also interesting to note here that galaxies with the lower stellar mass and metallicities are also those with the largest escape fractions, which are the bigger circle in the figure, suggesting that these galaxies are even more affected by the presence of the outflow, possibly shaping the low mass end of the mass metallicity relation. And finally, we also compare the average spatial distribution of the gas, dust, and star formation in these galaxies by stacking their C2 far infrared and UV emission. So here you can see the stacked images in the different bands and the corresponding radial profiles. And as you can see, the far infrared and C2 are more extended than the UV emission, confirming that outflows in these galaxies are really able to push the dust and the gas outside of the stellar disk, so enriching the circumgalactic medium. And I think I will leave you with the conclusions, and I'm happy to take any questions. Thank you.
Thank you very much. Very interesting. And a couple of questions. I see our first speaker there.
Hi, thanks for the great talk. So one of the slides you showed that you are using C2 to get the star formation rates, but also the gas masses. So I was wondering if that introduces a degeneracy, as in if you use the same tracer for both of them.
Yeah, so C2 basically traces all the phases of the ISM, so it can be a little bit tricky. In case of the star formation rate, we used a relation, let's say, between the C2 and star formation rate that was observed in the local galaxies, but also at high redshift. In case of the molecular gas, there is a different treating, let's say, of the C2 line. There is a relation also that connects the C2 to the molecular gas from Zanella 2018 and also from the same DGS galaxies by Madden, I guess. So we use different approaches, but in case of the atomic gas, we also made a correction based on the percentage of atomic gas present in the whole gas, let's say. So we accounted only for 70% of the gas to be in the atomic phase. So we took into account that kind of difference in the different phases of the ISM. Thank you.
Yeah, thank you for the talk. I'd like to repeat a question that was asked earlier this week in Focus Meeting, which is how you define the outflowing gas by fitting the Gaussian. For the integrated spectra of galaxies, there's no reason why the integrated profile should be Gaussian at all. After all, for more massive galaxies, we get very broad double horn profiles. So could you comment on the appropriateness of using that to define both how much gas is outflowing and at which velocity it's moving and so on?
So the question is if the method of putting a double Gaussian function is correct to measure in the outflow.
For integrated profiles of galaxies.
Yeah, so I think, of course, actually in the sample, we have also cases in which we have asymmetric profiles. So there can be also presence of broad component, but it's not symmetric as the one that I shown here. So of course, yeah, there's no reason for the main component, let's say from the galaxy to be Gaussian, but still it's some method that is usually used in the literature. So we could make some comparison with that. But I agree that, yeah, there's no physical reason to be Gaussian at all. So yes.
Bruce, you quick.
Yeah, very nice talk. For the extended FIR and C+, could that be in a disk, or are you sure that's in 3D?
Sorry, can you repeat?
Could this extended FIR and C+,
Yes.
beyond the FUV, could that be in a disk? Could that be an extended disk? Or does it have to be a three-dimensional distribution like an outflow?
So yeah, we only consider the stacked images and that were more extended than the UV continuum. We consider the UV continuum as the extension of the stellar disk. So from that, we claim that there can be some extended emission in terms of C2 and far infrared with respect to the UV emission. And there are also some other evidence. There is a paper from McCormick 2018. They also studied the dimension of the disk and of the far infrared emission. And they found actually that the far infrared is more extended than the disk, and that can be evidence for dust-driven winds. So yeah, based on No, it just made by stacking everything. We have some kind of measurement of the inclination of the galaxies. We are not very sure about that. We only measure the ratio between the major and minor axes. We found that more or less all the galaxies are close to face on. So when stacking, everything is averaged out, and yeah.
Thank you. You can possibly continue later.
Yeah, sure.
And thank you
Thanks
very
so
much
much.
for your interesting talk again. So next speaker is Lucia Armillotta, and she will talk us about cosmic propagation and feedback in star-forming environments.
Hello, everybody. During this presentation, I will present the main findings of our simulations about cosmic ray transport and feedback in star-forming environments. Among my collaborators, I would like to highlight Nora Linzer, who is here today and who will present her poster later today. Now, for those of you who are not familiar with cosmic rays, let me say that cosmic rays are high-energy non-thermal particles that are mostly produced in supernova remnants through shock acceleration. From direct observations of cosmic rays in the solar system, we know that cosmic rays, the spectrum of cosmic rays extends over more than 10 orders of magnitude in kinetic energy. The spectrum is dominated by protons, and the protons have basically the spectrum of protons is a broken power law that peaks at kinetic energies of a few GeV. Now, in the local ISM, the total cosmic ray energy density is comparable to the thermal, turbulent, and kinetic energy and magnetic energy densities. And this observational evidence indicates that cosmic rays can play an important role in the dynamics of the interstellar medium. Now, from a theoretical point of view, studying the effect of cosmic rays in galaxies is not trivial, because this requires connecting the kiloparsec scales of galaxies to the microscopic scales where gas and cosmic rays couple. In recent years, there have been several theoretical works showing that the extent to which cosmic rays affect the ISM dynamics is strongly sensitive to the treatment of cosmic ray transport in theoretical models. Now, as I said, cosmic rays and gas interact on microscopic scales, and their interaction is mostly mediated by the ambient magnetic field. As you know, cosmic rays are charged particles, so they stream along magnetic field lines and scatter off magnetic fluctuations with a wavelength comparable to the cosmic ray gyroradius. This scattering reduces the effective cosmic ray transport speed, allowing cosmic rays to couple with the gas. Now, how do we go from the microscopic scales where cosmic ray scattering takes place to the macroscopic scales of galaxies? Well, because the cosmic ray mean-free path is very short compared to other relevant length scales, in most studies of ISM dynamics, cosmic rays are treated as a relativistic fluid. Now, so far, most studies of cosmic rays ISM interaction have parameterized the transport of the cosmic ray fluid with a constant scattering coefficient, thus ignoring the microphysics of cosmic ray scattering. And you can understand that given the variety of conditions within the multi-phase magnetized interstellar medium, a constant scattering coefficient is highly unrealistic. So to address this issue, we recently proposed a physically motivated prescription for the transport of the cosmic ray fluid, where the scattering coefficient varies with the properties of the background gas. We incorporated this prescription within the algorithm for cosmic ray transport in Athena++ and used this code to compute the transport of cosmic rays within the Tigris MHD simulations modeling local portions of star-forming galactic disks. Here you can see a movie of the Tigris simulation modeling the solar neighborhood environment. You can see that there is stellar activity at play within the disk, and that stellar feedback drives multi-phase outflows out of the plane. Now, let me add that the original Tigris simulations did not include cosmic rays, so the transport of cosmic rays in this work is computed in post-processing. Now, we explored several Milky Way-like environments simulated with Tigris, but for the sake of time, I will talk about the solar neighborhood environment only. This plot shows the distribution on grid of several MHD and cosmic ray quantities taken from one sample simulation snapshot. And from left to right, you can see the gas density, temperature, velocity, ion alpha speed, cosmic ray scattering coefficient, and cosmic ray pressure. And I would like to highlight that the scattering coefficient varies over more than 3 orders of magnitude, depending on the underlying gas properties. And this challenges the common assumption of constant scattering coefficient. The scattering coefficient is very low in high density, low temperature gas, where gas is mostly poorly ionized, and magnetic fluctuations are efficiently damped by collisions of ions with neutrals. As a consequence, cosmic rays diffuse fast in the warm, cold, dense neutral medium comprising most of the galactic disk. So this means that the distribution of cosmic rays within the galactic disk is very uniform. On the other side, the cosmic ray scattering coefficient, sigma, is relatively high in the extraplanar region, meaning that, and where gas is mostly ionized, meaning that cosmic rays and gas are well coupled in this region. Now, let's move to a more quantitative analysis. In this plot, the purple line shows the mean vertical profile of cosmic ray pressure, while the other lines show the mean vertical profiles of kinetic, magnetic, and thermal pressure. And you can see that near the midplane, the cosmic ray pressure is in equipartition with the other pressures in agreement with the observations. Now, as I said, we take a post-processing approach to study cosmic ray transport rather than evolving cosmic ray and MHD together. But we can still use the outcomes of these post-processing simulations to make some prediction about the dynamical effect of cosmic rays in the ISM. Now, you may know that cosmic rays affect the gas dynamics by exerting pressure gradient forces on the gas. And an important question is whether these vertical cosmic ray forces can counteract the gravitational potential of the galaxy, thus supporting galactic disks and driving large-scale galactic outflows. Now, if we focus on the disk region only, you can see that the cosmic, unlike the other pressures, the cosmic ray pressure is relatively flat. So this means that cosmic ray pressure gradients play a negligible contribution to offsetting gravity within galactic disks. However, if we move at higher latitudes in the extraplanar region, cosmic ray pressure gradients are larger than other pressure gradients, suggesting that cosmic rays can play an important role in driving galactic winds or fountains. Now, motivated by this finding, we recently studied under what physical conditions cosmic rays can accelerate the surrounding gas. To address this problem, we carried out a set of idealized simulations of galactic outflows where MHD and cosmic rays are now evolved together. The initial conditions of these simulations are taken from the solar neighborhood simulation, Tigris simulation, with a domain extracted from the extraplanar region. So the one on the right is our simulation domain. And during the simulation, thermal gas and cosmic rays are continuously injected from the bottom of the simulation box. In doing so, we simulate the presence of a continuous outflow coming from the disk. And we explored 2 different types of outflows, either hot and fast moving or warm and slow moving. Both types are expected to be driven by supernovae into the extraplanar region. And we found that cosmic rays have negligible effects in hot thermally driven winds, while cosmic rays can efficiently drive flows of warm gas away from the disk. So let me focus on this second case. So this is a movie of one of the simulations where warm and slow-moving gas is injected at the bottom of the simulation box. From left to right, we have gas density, temperature, velocity, and cosmic ray pressure. And you can see that net vertical cosmic ray pressure pointing downward is present throughout the simulation, suggesting that cosmic rays can counteract gravity and accelerate gas against gravity. And this is confirmed by a more quantitative analysis of the simulation. In the right top panel, you can see the purple line indicates the time averaged change of gas momentum flux, while the orange line indicates the time averaged change of cosmic ray momentum flux as a function of z. Now, from the momentum conservation law, we know that in steady state, these two quantities must compensate, and this is the case in our simulation. In particular, the gas momentum flux increases with z, while the cosmic ray momentum flux decreases with z, meaning that overall cosmic rays are transferring momentum to the gas. And finally, I would like to show this second plot where the cyan line indicates the mean vertical profile of the gas velocity. And you can see that cosmic rays can accelerate warm gas up to 50, 60 kilometers per second within 3 kiloparsec from the disk. So since I'm running out of time, I will leave you with my summary slide. Thank you.
Thank you very much, Lucia, for this very interesting talk on the simulations with cosmic rays. And time for a couple of questions. Alberto.
So, yeah, thank you for the talk.
Okay.
I'm curious about how well does this couple to the neutral phases in this case, because you're not accelerating them directly with the cosmic rays. So.
Yeah, that's a good question, and I don't know the answer yet. I mean, this is gas with a temperature around 10 to the 4 K, so it can be a mix of neutral and ionized, warm neutral and ionized gas. We are now finally working on the Tigris simulations with because the simulation that I showed do not have a proper chemical network. So that's why it's difficult to answer your question, but we are now finally working on the Tigris simulations with an accurate chemical network, and then we can distinguish different phases of the hydrogen.
This may be asking the same question in a different way, but do you have, I mean, if you make aggressive assumptions, do you have a mass loading factor for what the cosmic rays might be doing out in the disk?
Mass loading factor at the...
Yeah, I mean, if you just took the star formation rate, that implies some cosmic ray generation, then you're lifting it.
Yeah, I mean, for these simulations of the solar neighborhood, at 3 kiloparsec, the loading factor is about 0.1.
Okay.
That is consistent with the loading factor of warm gas accelerated by a hot wind.
Cool. Thanks.
Okay, thank you, Lucia, again. And our next speaker is Alberto Bolatto, and Alberto will give us a talk about the James Webb Space Telescope view of the nearest starburst.
That's it. So thank you very much for allowing me to give the talk, or inviting me to give the talk. I'm going to tell you about this project. This may seem like an ill-advised idea, no? So you pick the most sensitive telescope ever, infrared telescope ever made, and then you pointed to some of the brightest objects in the sky in the infrared. But the reason for doing that is that, you know, they look like this, no? So this is the center of NGC 253. In the optical, NGC 253 is one of the two, you know, big starburst galaxies within 3.5 megaparsecs or so, one of the three. You know, you can see that the extinction is incredible, no? This is an example of a nuclear starburst. So the starburst is very centrally concentrated and is fed by a bar that is feeding gas into the center. The amount of star formation in the center is not that large. In absolute numbers, it's 3 solar masses per year, but that's concentrated in, you know, about 100 parsec area. Now, this is what that galaxy looks like to mirror in the infrared. And you can see that the galaxy becomes transparent the center is incredibly bright, and you can see this X-shaped, streams, and that's essentially the presence of a galactic outflow that we know of in ionized lines and also in molecular gas. And so the ionized cone of the galactic outflow is here, and it's outlined by these X-shaped streams in the infrared. And here you can see very clearly that you have two spiral arms and a bar in the center, and that the center is very, very, very bright. And in fact, I mean, MIRI is spectacular for these type of things. The dynamic range is such that it's very difficult to show, the quality of the images with only one stretch. So let's zoom in. We are just zooming into the center. Again, it looks like that. The center is hidden behind, 100 magnitudes of extinction in the visual, or more in some cases. And when you change the stretch and you look at the image of the center, that is what you see. So that is a starburst in the center of NGC 253. And what you're seeing here is, some of these sources over there are very, very compact, very, very massive star clusters, very, very young star clusters. So these are super star clusters, SSCs, that are essentially driving most of the starburst activity in a ring in the central regions. And you can see now the details of the cone. And by the way, we only see the front cone in the optical, but there is also a backside that is behind the galaxy, so you don't get to see. So now we have studied these superstar clusters in the center of NGC 253 using ALMA, very high resolution. So this is ALMA at half a parsec resolution, 0.03 arc-second resolution. And so there are papers in 2018 by Adam Leroy and 2021, 2023 by Rebecca Levy, characterizing the superstar clusters in the center. We know that these superstar clusters, some of them are extremely massive. You're going to see the numbers in a moment. And very, very compact. You can see it here. This is a scale, 1 arc-second, 17 parsecs at this distance. And what is interesting is that we have, of course, molecular gas data. And in the molecular gas, you see essentially P-Cygni profiles that are indicative of outflows in some of these objects. No? So in the infrared with HST, the only cluster that you get to see is that one, cluster number 5, and the rest are completely hidden. So these are the profiles in CS726, and these outflows are outflows that essentially are going to shut down that particular episode of star formation. The cluster will stop accreting gas because the outflow is just clearing it up. So these are distinct, these are local outflows distinct from the very large scale outflow that is coming from the entire central region. Now, one point to make is that even at these wavelengths, there is extinction, and it's not negligible at all. So you have to take that into account. Now, one thing that we can do is we have a spectroscopy too. And so we can look at the details of spectra from each one of these clusters. And you can see here, this is one example, is cluster 5. That's the cluster that's actually visible that was detected with HST in the near infrared, because it has excavated a cavity and it's shining through the cavity. And essentially, I told you that there are winds in molecular lines. The winds have something like 40 kilometers per second velocities. We can also see winds in the ionized lines that are present in MIRI MRS. And you can do the calculations. You need these two components to fit the lines. And then you see that this component, there is a blue side component, corresponds to an outflow, and the velocities are 300 to 400 kilometers per second in the ionized gas. Now, this particular cluster is a few times 10 to the 5 solar masses of stars. We have VLA data, so we know what the ionizing photon flux is. We can backtrack to the stellar mass. It has about the same amount of gas in it, and the size of this thing is 3/4 of a parsec in radius. No, so the interesting thing is that it's very difficult to overcome the gravity when in something that is so massive and so compact. So feedback doesn't work particularly well. And this seems to be, all these clusters are very, very young. And in fact, most of them, we think, are pre-supernova. So this is an example. Here, this is the SCD of that particular cluster done at very high resolution. And there is no indication for synchrotron. There have been also chemical studies. So that's Betsy Mills, chemical studies by Rico Villas, and which indicate the same thing. These are very, very, very young objects. So we think that what we're seeing here is essentially the mechanism that stops the cluster from growing further and is shutting down the star formation and is going to give the cluster its final mass. No? And this is very, very interesting to understand, because if you think about what is happening in very early galaxies, is some magnified version of this, essentially. No? So let me talk about the other starburst galaxy that we observed, which is M82. M82 is, of course, a host of one of these multi-phase galactic winds. It's very, very prominent. You saw it before I think in Michael's talk. And we have been studying the clusters and the outflow in M82. And I just want to show you the very center, because that's the data that came first. So we have a full analysis that is published. And what we're doing here is we're using NIRCam data to essentially extract the pH feature at 3.3 microns and show you what it looks like. And these pHs, at 3.3 microns, are the smallest of the dust grains. No? And because they are the smallest of the dust grains, they get destroyed instantly in hot gas. So this is a cold phase. What you're seeing here in these pictures is the cold phase of the wind, the base of the galactic wind in M82. And what is very obvious when you do these pictures is that it has this incredibly detailed structure of filaments superimposed. And the picture on the right is the same picture. It's just some unsharp masking type done on it, just to show you what is the structure of the cold phase in these winds. And we think that this is probably caused by shredding of cold clumps that are being dragged by the cold gas. And there are simulations showing the interaction between the hot phase and the cold clumps, and whether the cold clumps survive or not survive, depending on the details of those simulations. And so what this allows you to do is essentially test the mechanics of those simulations to understand how these phases survive and how you launch a neutral or cold wind. Because a cold wind is supposed to carry most of the mass up to the galaxy. So that's what you care about. So this is a paper by Dean Fisher. And what I wanted to show you here is that there are these streams, these plumes of pH emission coming from the central regions. And you can compare them with, in blue is a hot phase in X-rays. And in green is the molecular gas that we get to see in CO. And what you end up seeing is that as you move farther and farther up along the wind, there is a separation between the cold and the hot fluid. And finally, last slide before the conclusions, we've been also studying the clusters in the center of M82. So we have a very good accounting of the clusters in the infrared. This is comparing essentially an optical catalog with the infrared catalog. We see about 1,300 clusters down to masses of 10 to the 4 solar masses. And what we find is a distribution that is essentially compatible. Sorry, this is my own alarm. Dismiss. That is a cluster mass function that is essentially compatible with the mass function that is determined in the optical, but we have much better resolution. So we get much more precise sizes for the clusters, and we get more precise masses in principle. So just to close here with the conclusions, the background picture is a picture of R136, 30 Dorados, the cluster at the center of 30 Dorados in the LMC. So you can think of that as a much more evolved superstar cluster, no? And you see the stars there, you see the gas and the dust being cleared. And we are seeing now these same things in the core of the nearest starbursts. And there you have just essentially a summary of the stuff that I've been talking about. Thank you.
Thank you very much, Alberto. Questions for Alberto? Yes.
Thank you, Alberto. Very nice. I'm wondering about the relation between the large-scale kiloparsec scale outflows and the very central outflows you were discussing. So the large-scale outflows, they're thought to be driven by supernovae, right? Would that be an earlier generation? You know, like in M82, they're actually age determination of some of the clusters, which are tens of millions of years old. So what is the relation? Is this a previous generation of starburst, or just wondering?
So the large, yes, it's a cumulative activity, starburst activity going on over a long period of time. But essentially, what happens with the large scale outflow is that it's an overpressure cavity that you're inflating by injecting energy and momentum with these winds, with the stellar winds, with supernovae when they happen, and so you're pumping the cavity, and at some point it breaks through the layers of neutral gas, and then it's like you puncture the balloon and the hot gas escapes, no? And it drags with it the colder phases. But yes, that's a cumulative, essentially star formation activity going on over a long time. And some of the clusters in there do have supernovae, so they are slightly older.
Luca?
Thanks, Alberto. Beautiful data. So do you have a sense for the mass ratio of the different phases that you've shown as a function of distance between the cold, the warm, and the hot?
I can give you round numbers, but we don't. This is something that we really want to do well. So we hope that this data allows us to do it very well, because the fundamental problem is the CO is great for a lot of things, but there are a bunch of chemical effects that you worry about, and there is a fundamental sensitivity limit that we have with the CO observations, which is, should be overcome by this type of observations of the cold phase. Now, in this type of observations, you have to understand the distraction of pHs as they move out. And, people are starting to simulate those things. So there is a very nice paper by Elena Ricci and Evan Schneider, essentially simulating, what happens with the extraction of gas as in a wind tunnel simulation of a cloud. So the hope is that, all of these beautiful data motivates people who can do the calculations to do them well, and we can compare observations and calculations finally.
Thank you.
I have a curiosity, but I'll ask you later. Since we have to move with the next speaker. Thank you, Alberto.
Thank you.
Next speaker is Francesco Grieco. And he will talk us about experimental evidence of high temperature formation of H2 and cold water on PAH-like surfaces.
So good morning, everybody. I'm Francesco Grieco, last year PhD student at University of Ghent and Lerma Sergi in Paris. And today I'm going to be talking about my last two papers of my PhD journey. They're about experimental evidence of high temperature H2 and solid water formation on pHs. Yes. So first of all, since it's an experimental work, I actually want to show the mess of the real setup that we are using, but then it's important to actually stress on the schematic top view. And here I want to point at the three main parts. So the beam lines that are basically like our gas phase that we use to actually inject molecules in gas phase. So we have a microwave cavity that we are able to actually dissociate, create a plasma, so create atoms that are like aimed towards a sample holder that will be our surface, our dust grain connected to cryostat to like actually assess different temperature ranges. And then our main detection method is actually the QMS. So this setup actually allows us to mimic what is the interaction of gas phase and dust grains in the ISM. So for this work, since we are using like pH as a surface, we are able actually to sublimate coronine a specific pH using like this sublimation method with this oven. We are actually able to create a surface, a pH surface on our sample holder. So why pHs? We all know they're like abundant, they lock up to 10% of galactic carbon. They're very important, like they're partly part of like the dust grains, but also they're very important for H2 formation. They're very important for like the chemisorption effect and the catalytic processes. In the lab, usually like a standard approach is to use coronine, a smaller molecule. It's very easy to handle, it's small enough, but also resistant, and provides catalytic and chemisorption effect. So far, there were not experimental evidence, direct experimental evidence by using like pH surfaces to actually catalyze the formation of H2 and solid water. So the first project regards actually the high temperature H2 formation on Coronine. So why H2? We know it's very important in the universe for like the cooling agent for star formation, but also we know that the main formation process happens on dust, on like surface. And there are three main steps that are like the adsorption, the sticking on the grain, the diffusion reactivity, and the desorption, the return to the gas phase. The most tricky one is actually the diffusion reactivity, because we know that the dust grains can be too hot, so we can have actually the desorption before the diffusion reactivity of H atoms to find each other to form H2 and desorb as a molecular hydrogen. And we know so far that actually H2 should not form above 50 Kelvin up to 100 Kelvin. The other point is that until which temperature H atoms can actually be stabilized through chemisorption to actually find each other, react, form H2 and desorb. Also in this case, like it was thought to be like max up to 100 Kelvin. So as I said, formalism allows us to, this is like the acronym for the setup, allows us to actually study the interaction between gas phase and dust, mimicking the ISM. So we are able actually to provide a direct experimental evidence of H2 formation on pHs up to 250 Kelvin. So this is more or less a schematic view of the experiment. And then like this is the schematic configuration. So the schematic configuration is made up of two main steps. The first step is this one. So we have to know how many atoms we're actually sending to the surface, that they're gonna find each other and form a molecule. To do this, we rotate the QMS in front of the beams. We have like the blue beams is like the molecular beam, and the purple one is when we dissociate. So we are sending atoms. The difference in signal of the QMS when we are sending molecules, where we are sending atoms, is actually give us the dissociation efficiency, the amount of atoms we are sending that we are going to be using to calculate the amount of molecules that are actually formed. So here we go to the second configuration setup. We turn now the QMS in front of the surface of the pH, and now we want to know how many molecules are desorbing from the surface, reaching the QMS after sending the atoms, the purple beam. So we know how many atoms we are sending, the dissociation efficiency. We know with the blue beam how many molecules we send, how many molecules we actually collect, the total. And so now we are actually able to calculate the amount of molecules that are formed after the interaction of the H atoms on the surface. So we have like something that looks at more or less like this. We have the highest efficiency that is in agreement with like previous literature, highest efficiency around 20 Kelvin for H2 formation on dust grains. And we have like a drop at 10 Kelvin that is not in agreement with literature, because in literature there were like mostly models, but in reality in experiments at 10 Kelvin, we already have the sticking of the molecules of the H atoms on the surface. So we have less catalytic effect from the surface. So we have this drop at 10 Kelvin. While the most important part and result of our work is actually the fact that we have a high efficiency of H2 formation on Coronine up to 250 Kelvin. Actually, the main result is that this is above already 50, 100 Kelvin. So I don't know what I did. Oh. Okay. And so I guess each of you might have like a different implication and application for like the high temperature of H2 formation on pHs. For us, the fact that it can form above 100 Kelvin was really interesting to see if actually there is an effect on the dissociation front, on the location of the dissociation front in a typical PDR picture, if like a warmer H2 forming might actually shift the dissociation front towards the ionization front. But also we know that we have a lot of dust above 20 Kelvin in high redshift clouds, star formation is happening, so H2 should be actually happening as well. And of course, it's always important to like for the interpretation of like the new data. The second project regards the high temperature formation of solid water on dust grains. We are basically introducing oxygen to the previous equation. We know also in this case that water is very important for the ice layers and also for like component for life, like astrobiology and so on. And we know that like in solid state, the surface reaction and pathways are like mainly three. That is the hydrogenation of oxygen, hydrogenation of O2, and hydrogenation of O3. And so far, also in this case, either like the experiments were like on surfaces that were not actually dust grains, or up to max 10 or 50 Kelvin. So what we asked ourselves is, okay, if we introduce oxygen in the equation with hydrogen, is oxygen going to be locked up in the grain, cause grain growth? Are we going to form ice as soon as hydrogen is available? So, and which one is the role, of course, of coronin and the temperature? So we studied interaction of oxygen and hydrogen with coronin up to 100 Kelvin. In this case, we obtained something like this. What I show here is actually the area, so the amount of water we are able to collect, therefore like form, by sending the same dose of oxygen and hydrogen at different temperatures. Why this dose, why this method is actually optimized, you can see it in the paper. Of course, I'm going very briefly through it. After optimizing this dose, but actually also after checking what happens if we send the atoms separately at different temperatures and the amount of water we collect, we are able to obtain this plot in which actually we see the max efficiency at high temperature as expected. We have like oxygen, hydrogen, residence time, they stay there, they can react, and we have the three formation pathway at stake. At low temperature, we have hydrogenation of oxygen, O2, O3. Around 40 Kelvin, O2 desorbs. We have the first drop because we have literally one pathway less. But the fact that we have water formation above 40 Kelvin means that there is absorption. Oxygen and hydrogen are stabilized on coronin. This can still happen. The last plateau above 70 Kelvin is the lowest because also 3 is desorbing. So out of the 3 pathways, we have only one left, that is hydrogenation of oxygen. But like this is the big novelty of these experiments. We are able to form solid water on pHs up to 100 Kelvin, 85 Kelvin. And this also stresses like on the catalytic role of coronin, the absorption effect of pHs. So this is like the main takeaway. Also in this case, several implications. For us was very interesting to see, like we know that while going from diffuse to dense clouds in translucent regions, we have like more or less a 40% of oxygen depletion that goes into a solid form we don't know yet. So for us, by like trying to reproduce in terms of temperature, this environment was just a way, another hypothesis like, okay, oxygen could form ice at higher temperature. So it's like one more hypothesis for like the disappearance of oxygen in translucent region forming ice at higher temperature, but also like could be another reason why a pH also seems to disappear in this region. They could be starting to be covered by ice. And also, of course, this still stresses on the chemisorption effect and catalysis of pHs for the formation of molecules at high temperature. So I just want to thank all my group and university, and I leave you with the takeaway message. And if you want to scan the paper, there are more details. Thank you so much for your attention.
Thank you very much. So question for Francesco? Yes.
Hi, great talk, thank you. I'm interested you mentioned OH radical on your slides. How much of the oxygen in this phase is caught up in the OH radical as opposed to like H2O?
How much oxygen? Sorry?
Yeah, and in your last slide about talking about the oxygen abundance, how much of the oxygen abundance is in the OH radical in this diffuse phase?
OH radical, like, so we are not, like experimentally, we are not like producing radicals OH. And we don't have like...
Okay, maybe I misunderstood the plot. I'll ask offline.
No, like, yeah, I don't know. Like we are able, we see that like there is, I think, 1/3 or 1/4 of water that is actually formed with respect to the amount of oxygen that is sent, because of course the stoichiometry is 1-to-1, amount of oxygen to water. Also because like a part of it is already returned to the gas phase. Like you have to consider that this efficiency are the efficiency that we are able to collect after forming water and desorbing it. But there is even more water formed that could be happening also through OH radicals, but we are not able to actually study OH radical. We don't have like this type of the setup. It would be like a way, like a faster way. I think would need spectroscopy.
Right,
Yeah.
thanks. Actually, I think that answered my question.
Bruce.
Does the increased temperature that you find for H2 formation allow H2 to form faster on interstellar grains? Because right now we think it forms quite slowly.
So with our setup, we cannot, of course, like study the kinetics exactly. What we tried to do, for example, was to introduce like the temperature into kinetic equations, but like the change of like temperature for H2 formation on dust. And we tried to do also in the application of like the location of the F in PDR. So by using, for example, cloudy and like to change the kinetics of H2 formation on dust. What's the problem is that we did not see with like a very basic implementation, a big change, so a faster H2 formation, therefore like effect, because like a lot of models still use like gas phase equation for like, so there was like one parameter for the modified Arrhenius equation that depends on dust. We tried to change it, but also like it was like a bit different, a bit difficult to assess it because like actually the equation is based on gas phase models.
Okay, thank you. Sorry, we have to move on. Thank you again. And from interstellar medium topic, we now are going to hear something about stellar population, and in particular, Thomas Nordlander will talk us about the oldest stars in the Large Magellanic Cloud.
Thanks so much. Thank you for that introduction. Thank you all for being here. So I will be talking about work led by my PhD student, Wei-Shen Oh, who couldn't be here, but I encourage you to have a closer look at the paper if you're interested. So starting with the big picture, I would like to think that the oldest stars are probably the most important part of the universe. So in this sketch of the timeline of the universe, we start at the Big Bang, where only the very lightest elements, hydrogen, helium, and lithium, were formed in very small quantities. And the properties at the very start of the universe were encapsulated in the cosmic microwave background. So with simple cosmologies, if you measure off your parameters from the CMB, you can recreate to quite high accuracy what was actually produced in the Big Bang. And skipping forward 100 million years, the first stars were born. These are probably very important reionization sources. And crucially, when they exploded as supernovae, they released the first heavier elements. So in your periodic table, this is when we move from the first row with hydrogen and helium downwards through rows 3 and 4 and 5. So especially the iron peak. From these ejecta, they mixed into the ISM. From this, you form the next generations of stars, and especially the second generation of stars. These are probably the oldest stars that we can see today. So this was outlined in the plenary this morning, that because the first stars were short-lived, probably very few formed in each galaxy, we have not high hopes of actually catching them in action, but the second generation stars, some of those are alive today, and they probably formed in much greater numbers. And of course, the second generation stars, they formed the first galaxies that are still around, that we see in these beautiful James Webb Space Telescope images. And off the scale of this whole image, that's where we are, right? So everything that happened beyond this depends on what happened in this image. So the properties of the first star is probably crucial to all of astronomy. And the way that we can use the second generation stars to understand the beginnings of the universe is shown in this figure on the left, that is showing the final state of a star as a function of its mass on the x-axis and the metallicity on the y-axis. So if you focus down on the bottom of this diagram, these are the lowest metallicities. For stars that would have had a mass between maybe 10 and 40 solar masses, we think these exploded as core collapse supernovae. We think that very low metallicity stars were unusually compact. They were difficult to explode. And typically this means that the supernovae that exploded would have been faint. So the ejecta would have had a hard time to actually escape the neutron star or the black hole that formed, and the explosion would have been faint. There's probably a bit of a desert between 40 and 100 solar masses where stars are extremely hard to explode. The only thing that can explode would have been hypernovae. And we know from the present day universe that hypernovae are rare. So probably most of the stars that form there are censored by the universe, and they would be very hard to see any traces of. And then around 100, 200 solar masses, those stars would have exploded as pairing stability supernovae. And on the right, I show the prediction of the observable signature of these in second generation stars, that the faint supernovae would have produced a lot of carbon, not so much iron. The hypernovae would have produced a rather flat abundance structure, but with a strong odd-even pattern, and maybe a surplus of zinc. And the pairing stability supernovae would have also like a very characteristic abundance pattern. So by observing the oldest stars that are alive today, if we are able to identify these abundance patterns, you can match them up to, this star formed from gas that was enriched by a faint supernova that must have had a mass between 10 and 40 solar masses. And we can recreate what was actually the mass distribution of the first stars, which people like Dioshard are trying to predict. So this is a nice complementary observational complement to the theory there. In the LMC, I'm jumping right to the end, actually. These are the results of my student Wei Shen O's final PhD paper, where I'm showing the location of the most metal-poor stars known at the time in the LMC. They were discovered using sky microphotometry, and I'm showing the metallicities in Fe on H here. On the right, I'm showing the abundance pattern of each star that he studied. So the symbols are showing the abundance for a given star. Each panel is a given star. Each symbol is the abundance of a given element. And the line you're seeing, those are the average abundances in the Milky Way at that metallicity. So if the symbol is above the line, then the star was rich in that element. If it is below the line, then it is poor. If it's highlighted in red, then it deviates by at least half a dex. So a factor of 3 or more, it's a strong deviation from the abundance that you would expect. And the take-home message, the first take-home message is that each star at these metallicities, all the stars that we found in the LMC, is a weirdo. They all have at least one element that is discrepant from what you would expect from the average abundances seen in most stars. So starting from the top, that one has an unusually high barium to europium ratio. The next two are enriched in neutron capture elements, specifically according to the rapid neutron capture process, the R process. The next one is rich in zinc, which I just mentioned. It's poor in strontium and barium. And then toward the bottom, those are rich in aluminium and nitrogen and sodium and so on. Each one is a weirdo. So the early chemical evolution in the LMC, one of our nearest dwarf galaxy neighbors, was very inhomogeneous, even at metallicities that are -2.5, -3, which in the Milky Way are not really considered interesting anymore. We can tag these even. So this is the key, right? Bringing us from the second generation stars back in time. So the top one, this high barium to europium ratio, that's exactly what you expect from spin stars. So spin stars are zero metallicity stars, extremely compact things, could have been quite massive, would have been rotating very rapidly, much more rapidly than we can see today, maybe 500 kilometers a second. And this produces deep mixing. It can lead to something akin to an S process. And specifically, this would produce a lot of barium, but no europium. If we skip down to about the middle of the page, that hypernova, this high zinc, that's thought to be the smoking gun of hypernova explosions, and at the same time, very little strontium and barium production in that star. And toward the bottom, this nitrogen and sodium-rich star, that's probably the signature of a fast-rotating massive star. Might not have been one of the first stars, it's a zero metallicity star, but definitely a low metallicity star, rapidly rotating. So using the samples like these, and you will hear more from Annie Chidi on Monday with a similar sample going even deeper, you can start tagging individual stars back to the enrichment processes in the early universe and the properties of the first stars. The second thing I'd like to talk to you about is specifically the R process. So this is a beautiful summary of the abundances of R process elements in dwarf galaxies from 8 years ago, still valid though, by Alex G. On the left, we're seeing barium, and on the right, we're seeing europium as a function of iron abundance. So both are produced in neutron capture processes, and I want to draw your eyes toward these stars that lie well above all the others. They are enriched above some kind of what we think is a basal level of neutron capture processes. Something happened at some point in this particular dwarf galaxy, but not in any of the others. After some of the first most metal-poor stars known in that star and that galaxy were formed, so at a metallicity of about -3. So there's some kind of delay time before this happened. To me, that smells like neutron star mergers. These things are predicted to be rare. They have a delay time. By coupling these observations to chemical evolution models, you can pin down when did this actually happen. And thanks to the observation that happened in 1 out of 10 dwarf galaxies, ultra-faint dwarf galaxies, you can try to figure out how often does it happen. So this is the picture from these ultra-faint dwarfs. These are very low mass systems, right? The LMC is like 1/10 of the Milky Way's mass, so it's a bit different. But we're seeing something similar. So if I again draw your eyes toward these europium-rich stars, by the way, these abundances are a compilation from Wei Shen O's paper and Annie Chidi's paper and previous work. The gray symbols are the Milky Way values. And you can see that these circle values, those stars are enhanced by 1 or 2 dex in the R process. So something happened after a delay in the LMC. Stars more metal poor than about -3 do not have almost any neutron capture element abundances in them. At about a metallicity of -3, some of them start showing these elements. And I think it's something like this, that the most metal poor stars, they formed before the first neutron star mergers. We're seeing some kind of gray transition period where the LMC formed from many systems that merged, right? So some of them saw neutron star mergers and some did not. And beyond that, in the white region, those had all experienced neutron star mergers. And because the chemical evolution was so slow, it's at a level that is much higher than the Milky Way. So this is my second take-home message for you all. And with that, I would like to encourage you to have a look at the paper, and I'm happy to take questions.
Thank you very much. While we wait for the questions, yes, I see already Alberto, I would like to have the poster presenters here next to me.
So concerning the great talk, concerning the inhomogeneity of these stars in the LMC SMC, I'm just curious how many progenitors contributed to enriching that star, because presumably you can make it up with a combination of the different types of contributors.
You mean how many stars contributed to each abundance pattern that we're seeing in a given star?
That's correct. I mean, they have an iron abundance of -3 or so.
Yeah.
So how many generations do you need to get to that iron abundance, and then how much can you play with the contribution from the different types of stars?
For some of these, you can do it with one supernova. So for the hypernova, you can get all the way there with just one explosion. The others, it's a little bit hard to say if it's just one explosion or if there might have been a mixture of multiple. It's possible to play those statistics, and we're hoping to follow this up and put that together.
Thank you for your talk. This might be a bit of a naive question, but I was wondering how the peculiar abundances that you presented relate to alpha element enhancement.
Effectively, all these stars are enhanced by roughly the same amount in alpha elements. So they all have about the same oxygen abundance, but they have different carbon abundances, for example. So if you believe carbon is an alpha element, then they are all very different. If you think oxygen is the true alpha element, then they are all about the same, actually.
Do we have any poster presenters in the room? Yes. Can you come please next to me? Okay, well, very quick.
Thomas, nice talk. It's a very good question. So is the statement that the non-R process enhanced stars are accreted and the European enhanced ones formed in situ in the LMC, and that's what explains the difference? And they're not enriched in situ by neutron star mergers in the LMC environment.
I like your scenario. I'm not sure I can say though.
Yeah.
And I'm not sure we would tell the difference with just this, but I mean, we would expect that the LMC formed from multiple systems that had merged. Right?
Okay.
Yeah. So that's as much as I'm willing to say.
Okay, thanks.
Thank you.
Thank you very much again. So just in the last 3 minutes, so we are going to have a flash poster presentation. We have 3. So we proceed with the first one, and then second and the third. Okay. Yeah, go there. And advance by 1. I'll do it.
Great.
Your poster.
Okay.
Yeah.
Hi, everyone. I'm Dinesh Krishna Rao, or DK. I'm an assistant professor at Colorado College in the US. If you need to find me quickly, astronomy.dk is my website. My poster is about the Fermi bubbles. We found optical emission towards the Fermi bubbles as a way to map out the Fermi bubbles in emission. Also have done it in the same direction where UV absorption data exists, so we can combine absorption and emission to probe in situ characteristics of the Fermi bubbles and the ionized gas there. And we've also tried looking in radio recombination lines unsuccessfully, but we still learned a lot of information about it. So yeah, check out the poster online or talk to me. Thanks.
Thank you. No poster presenter for this? Okay, he's not here, then next.
Good morning. My name is Annelise Algebert, and today I would like to talk about one of the projects that we are doing on the GATUS survey. So GATUS stands for Galactic Activity Torus and Outflow Surveys, but it also means cats in Latin language. And the GATUS sample consists in nearby Cipher galaxies that we have high-resolution ALMA observations presented in Garcia Burrillo 2021 and 2024. And in this project, we would like to use spatially resolved molecular line ratios in order to trace changes in the gas excitation due to AGN ionization or jets. In order to do so, we use ALMA and JWST observations. And in the bottom figures here, I show the preliminary results for the cold molecular gas using CO322 and CO221 observations. And the third plot shows the line ratios is enhanced in regions that are co-spatial with the hotspots of the radio jet traced by the contours. And this is also found in the MRS JWST observations using the warm molecular gas. And these results were published recently by Davis in 2024. And this study case illustrates that radio jets interacting with the gas induce distinct gas excitation conditions. And this is a phenomenon that was explored so far only in a few detailed results studies. So if you're interested, have a look at my poster and the recent results from the ALMA and JWST results from the GATUS. Thank you.
Okay, that's it for today's first session of Division H. So I would like to thank all the speakers of this morning session. So thank you all, and I'll see you at 1:30, the same room as this morning.
Hi, everyone there. I'm not sure you can hear me.
Number 2. Victor, if you hear me, just unmute and we'll see if we can hear you.
I'm not muted, and I try to test it, but I should have the right to share then.
There you are. We can see you.
Yeah, okay. Okay, so let's try to
That's
start.
it.
Yeah.
So you'll just go to full screen. So successful test. We'll turn you off now.
Yeah.
Full screen. We see it.
All right. Thank you.
Poster presentations. If you have a poster, and if you have sent me, my name is Edvige, a slide for the flash presentation, then you get half a minute of time at the end of this session to present your poster, and you'll find your poster on the screen. If you have not sent me your poster, then there is nothing we can do. Okay? Yes. It's the Dropbox. Yes, it was the Dropbox. So. It's different than the Oxford platform. That's for the poster session. So 2 separate things.
Welcome to the second session of Division H talks. We will begin again with Monica and another prize award for PhD prize. And then Charles will continue with his first talk.
Okay. Thank you, Bruce, and welcome to the afternoon session. It is really for me a pleasure and to hand the 2023 PhD diploma for the winner, which is Dr. Charles Law. He did his PhD work at Harvard University with a supervisor Karin Orberg. So please congratulate Charles.
All right. Hello, everybody. I guess while waiting for the slides to say hello, my name is Charles Law. I'm a Sagan Fellow at the University of Virginia, and I study protoplanetary disks. So we'll get started once this pops up. But I just want to start by thanking my PhD advisors for their steadfast support, Karin Oberg and Chizu Zhang. I also want to say that the work I'm going to be talking about today is really, let's see how, oh, wrong one. Green one. Okay. Thanks to my PhD advisors. Thanks also to all of my collaborators. So really the work that I'm showing is not just my work. It was really only possible with the help of all these great folks and many more. And lastly, and most importantly, I want to thank the IAU for having me here today and to be able to share this work with you. So as I said, I study protoplanetary disks. These are the birthplaces of planets. They're swirling disks of gas and dust. But importantly, they're the last stage when we have substantial reservoirs of primordial molecular gas. And so they're really ideal settings to study the chemical conditions during the epoch of planet formation as we move from the disk to the full planetary system. And we know that planet formation is often well underway in these systems, so we can really directly observe the environment from which planets are assembling. So there is one problem, which is that these disks often have very complex small-scale structures. You can see that here illustrated in this schematic. We're talking a few tens to 100 AU scales where we have gradients in the gas temperature, in the gas density. We have a variety of dynamical processes, such as the dust drifting, vertically settling. You have the presence of major volatile snow lines, such as water and CO2 and CO, all of this happening in a very small space. But all of this physical conditions is going to impact the type of planets that you actually form, depending on where they are in the disk. So we really need to zoom in and understand this structure in detail to understand planet formation. So I really want to say that ALMA has been the transformative facility that has let us see the molecular gas in these disks at high spatial resolution. So let me just take you back to about 9 years ago. This is an image of HCN, the molecule HCN, hydrogen cyanide, taken with the submillimeter array of a famous protoplanetary disk. What you can see is that there's bright molecular line emission here. There's tons of gas, but the observation is very spatially unresolved. We're dealing with a beam size that is several arc seconds, which is roughly the scale of the disk. And so what this means is we have a variety of outstanding questions. What is the detailed radial and vertical distribution of the gas? How common are substructures? What's the chemistry like in the inner planet forming zones? And how does planet formation actually change the chemistry that we're seeing? To really drive this point home, here is the scale of our solar system on this image. And when I started my PhD, these really nice images that came out with ALMA looking at the millimeter dust, that is the planet forming material in these disks. And you can see when you use ALMA, it's a really beautiful image. You see lots of rings and gaps, and we're really zooming in down to that planet forming zone in the dust. So my whole thesis is centering around what happens when you take ALMA and look at the molecular gas. And here's a short sneak peek of that. You go from an image here where you're basically unresolved to having a very, very highly resolved, beautiful image. This is the same disk in the same molecular line. And now you see emission much further out, and you see 4 distinct rings that are very spatially resolved. If you just look at the beam size there, we've done a huge improvement compared to the previous observations. So the way I've structured this talk is to really provide you 3 vignettes, 3 case studies of what we can really do, what kind of science we can achieve by going to ALMA and looking at molecular gas in protoplanetary disks. And I'm going to start by talking about the radial gas structure. So this observation that I showed, this image, was taken as part of the MAPS program, Molecules with ALMA at Planet Forming Scales, a large program around 100 hours with ALMA, led by Karin Oberg, but a large team of astronomers, nearly 40 astronomers across the world. We published this in 2021, and now it's up to, I think, 23 papers from the MAPS team and another 10 plus that are using our data, which is all publicly available here, including all of the scripts to make all of these images. But the main aim of this program was to do a chemical survey at 10 AU scales in 5 protoplanetary disks. They're shown here. These disks all have dust substructure and have indications that planets are actively forming inside of them, making them perfect targets for this kind of work. So what I'm going to show you is just a gallery of some of the results. So each row here corresponds to one of the 5 disks, and each column is going to correspond to a different molecule. This is the dust, and here is 12CO, but we observed many different molecules. You can see here just a fantastic gallery of everything that was observed as part of the MAPS program. And besides being very beautiful images, you can see a few things. A pretty remarkable diversity in the morphology of the line emission. If you just look across the rows or down the columns, you see that each disk looks different in different lines. You might also notice there's some substructures here. We're seeing rings and gaps. But for those people that don't look at these particular lines, don't study protoplanetary disk chemistry in detail, I just want to recast this a little bit. We picked these particular lines to tell us something about either the physics or the chemistry in these disks. In particular, the CO lines gave us access to the gas density, The hydrocarbon molecules trace the carbon abundance. HCO plus gives us ionization. CN radical tells us something about the UV field, and the combination of HCN and DCN give us the D to H ratio in these disks. But I want to talk a little bit about this variation. So if we just choose the same molecule, here's HCN again, hydrogen cyanide, and we look at the emission distribution shown in integrated intensities here, what you can see is that from disk to disk, there's a huge amount of variation. This is the same molecule, but it all looks quite different. Some disks have multiple rings, some have one ring, some are centrally peaked. This variability also occurs in the intensities. You can see that some disks are incredibly bright in the HCN emission and others are faint. So looking from disk to disk, we see a ton of variation. What we also see is substructures. They're ubiquitous. We find in the 18 brightest lines that we looked at over 200 substructures in the gas. That is 200 rings, gaps, emission plateaus, or shoulders, which you can see here that we characterize by fitting the profiles. The main takeaway here is basically at every radii in these disks, we see substructures. We see them in all types of molecules, and we see them down to our resolution limit. Moreover, we don't find any one-to-one links with the millimeter dust features or the major molecular snow lines. And so the big takeaway from this first project was that the planets that are assembling in this disk are likely assembling in very chemically rich environments, but very distinct environments, depending on which disk they're forming in, and even at what radius in that disk that they're forming. And that we don't have a single nice explanation for the ubiquity of these substructures. It really likely is a complex interplay of chemistry and gas physical conditions that are occurring in these disks. Okay, so let's move on from the radial direction to the vertical direction. And it turns out we can now begin to see these protoplanetary disks in their full three-dimensional glory. So we know that the most molecular line emission in protoplanetary disks is not coming from the midplane, not coming from the region where planets are forming, but it's coming from an elevated warm molecular layer. This is a layer in the disk that has gas temperatures warm enough and gas densities high enough that we can have the existence of gas phase molecules, as you can see here. And we care about locating this vertical region from which the lines are coming from for a variety of reasons. We need to know this if we want to use gas kinematic signals, which people use to find protoplanets, measure stellar masses, make turbulence measurements, and so forth. We can also leverage this technique to measure the two-dimensional gas temperature in our disks, which I'll talk about a little later. And it also has profound implications for the chemistry of planet formation. If we're using molecular line emission, like I showed before, to measure abundances, we would like to know how close those abundances are actually to the midplane where planets are forming. Can planets actually see the abundances that we're measuring? And we know this is the case. If you look on edge-on disks, there's a really nice image from ALMA, but edge-on disk, you can clearly see that the 12CO emission is coming from an elevated region here. It's not coming right from the midplane. So this matches our expectations very nicely. But the disks from MAPS weren't edge-on disks. They were inclined with respect to the observer. And so the schematic down here is showing you what these disks look like. They're inclined. You have the midplane in this gray region here, and then you have two conical surfaces. These are the elevated regions from which the line emission is originating. Here I'm saying this is the CO because we can look at the channel maps, that is velocity slices of the emission. And we can actually associate various slices in the channel maps back to our schematic picture here. So we can see that very nice Keplerian rotation in terms of a butterfly pattern. You can see the blue side going to the red side. But the main point that I want you to take away is if we choose the correct channels here with such high spatial resolution observations, we can actually see directly the height from which the line is coming from. We can see that upper conical surface as well as the lower conical surface in the midplane in the middle. And the fact that we can actually see this means that we can write code, which we did as part of MAPS, to robustly extract the emission heights. That is the region in the disk vertically from which the CO is originating from. And just to stress, what we're measuring here is essentially a tau equals 1 surface. That is, we're looking down until the line becomes optically thick, and then we're measuring that height. And we can play this game not only for 12CO, but we also have the isotopologues. So we can do the same thing for 13CO. And what you'll see is the surface moves down. That's because 13CO relative to 12CO is less abundant, and to get to tau equals 1, you go further into the disk. And correspondingly, the surfaces move closer together. You can play the same game with C18O, even less abundant isotopologue, and now you're essentially down to near the disk midplane. What's particularly powerful here is now you're tracing from elevated layers down to near the midplane. And because we expect these lines to largely be optically thick, if you just read off the intensity values here, you can convert those to an estimate of your gas temperature. And now you have an empirical measurement of your gas temperatures over your full height of your disk. And this is done in an model-independent way. It's just by extracting the heights and assigning their associated intensities. And this was a technique that we were able to employ for all 5 MAPS disks. So it's a very general technique. If you have observations of these quality and you have an inclined disk, you can make a direct empirical measure of its 2D gas temperature. Okay, but this technique is also pretty general. So we spent a lot of time getting this to work well for the MAPS data. And then we asked the question, can we actually go back and look at some other disks that were in the ALMA archive? And so the answer is yes. So here is a giant gallery of around 20 disks or so from the archive showing their 3-dimensional 12 CO surfaces to really just emphasize the point that we're now really seeing 3D disks. And so this was work that I led myself, as well as some members in the community here using both our tools, and people have developed their own tools to do this. But the main point is that we have sufficiently large samples that we can actually begin to explore that vertical emission distribution in a more statistical way. So just the big takeaway here is that we now have improved techniques, which when we combine with our high angular resolution observations, we can get a full 3D view of the molecular structure of planet forming disks. Okay, so my last few minutes, I just want to talk about the one last part of my thesis, which is potentially one of the most exciting, and that is to focus on how we can find planets using chemistry. So why might we be able to do this? If we have a giant planet, that is a few Jupiter masses, embedded in a protoplanetary disk and forming, we expect that that planet to be locally heating the gas right near where the planet is forming. This heating is going to be localized both radially and azimuthally. So that means it should be an asymmetric heating that should trigger chemical changes that we can expect to see with ALMA, that is driving new hot gas phase chemistry and the sublimation of ices. So we might see new molecules at this location. I want to introduce this disk quickly, HD 169142. The main thing to take away is it's a face-on disk around a Herbig star. But the most important thing is that it has evidence of a giant planet, 1 to 5 Jupiter masses at 40 AU. The planet is located right here. It is carving out a gap in both the gas and the millimeter dust. And in fact, there have been observations in the near infrared that have detected this planet as a point source and actually seen it orbit in a Keplerian fashion across multiple epochs. So we have good reason to believe there's a planet right there. So what I did was I went into the ALMA archive. And so here's a nice millimeter dust image of this disk. So here's where the planet is located. First thing we saw was we detected SO. SO is a molecule we don't often detect in these kinds of class 2 protoplanetary disks. What we were really excited about is there's this detached blob sitting right next to where the planet is. Next, we tentatively detected SIS, a molecule that has never been seen before in protoplanetary disks. Very non-Keplerian, very asymmetric, this arc-like structure connecting with the planet. So we kept looking. Turns out we also found a 13CO point source, right where the planet is, detached from the expected Keplerian rotation of your disk and blue shifted. It's this region right here in the spectrum. We kept looking. We found 12CO at the same location here, another detached blob in emission. So if we put this all together, it means in this disk, with pretty good evidence of a planet, we see 4 separate chemical features all peaking in the same vicinity of that planet. And the fact that we're seeing molecules like SO and SIS, this is telling us that there is some energetic phenomena happening here. These are typically shock tracers in other ISM settings. So what we think is happening here is that the planet is driving a shock or driving an outflow, and we're seeing the chemical consequences of that. So big takeaway for this is that we can use molecules that we haven't traditionally looked at in disks, such as SO or SIS, and they might give us a new way to detect and potentially characterize giant embedded planets. Okay, so that wraps up my 3 stories from my thesis, but I just want to end by saying that I think the future is bright, and I hope that I convinced you that by using these sensitive, high angular resolution observations with ALMA, we can learn a lot. And I think this is validated by the fact that there are 5 ongoing or recently accepted ALMA large programs focused on the gas content of protoplanetary disks listed here. And in a few years, we really will be able to have a statistical sense of the disk chemistry. If we combine these together, we're going to have over 100 disks with their chemical characterization performed by ALMA. So I think the future is quite bright. We'll be able to continue doing a lot of this science. So just to wrap up, high-resolution ALMA observations are powerful probes of planet-forming settings. In my thesis, I mapped the radial and the vertical gas structure and potentially showed how we can use chemistry to actually trace planets in these disks. All right, thank you very much.
Thank you very much, Charles, and congratulations again on your PhD prize. Do we have questions? We have 5 minutes for questions. Yes, over here.
Excellent work, thank you. I have a question on the third part about the planets. So how do you explain the difference between the distributions of SO and SIS?
Yep, so we think that the SIS, so you need to get the silicon off the dust grains. So that is probably related to an outflow or a strong shock for that to make that happen. The SO we think is probably ice sublimation. And this is also confirmed by the kinematics because the SIS and the CO lines, they're all blue shifted. That tells us they're probably in the outflow, whereas the SO is actually not different than the Keplerian rotation. It's just spatially offset. So we think there's just a warm spot that's sublimating some sulfur-rich ices that's producing the SO. And we think the other three features, including the SIS, are probably a much more energetic event.
Yeah, really nice talk. My comment is on the outer edge of the disk, the upper and lower part, which you say is warmer gas, makes sense, but that gas is also illuminated by the UV radiation of the star. So there's going to be photochemistry and photodissociation of various molecules. So has that been taken into account? It's not just, I think, not just warmer gas, but also photodissociated gas.
Yes, that's definitely true. And I think that there's actually the IM loop disk in particular. It goes out to around 1,000 AU in radius. And is known to be suffering from this. So we sort of truncate how far we actually go out in the 2D temperature maps to try to avoid that a little bit, but you're right. It's unavoidable that that is going to sort of be a confounding variable in the outer regions.
One more question. A quick one from me. Do you notice the rotation curve changing with height?
Oh, that's a great question. I haven't personally led the rotation curve efforts, but you need, in fact, you need the heights to actually measure the rotation curves. So there's a whole sort of industry, which the ExoAlma program, the large program, is doing. They need to measure the heights first to be able to accurately fit their rotation curve. If they don't take the heights into account, they get skewed rotation curves. So it's sort of they have to measure the height first to do that.
Well, let's thank Charles once again. The next talk is by Naval Badari on the formation of massive stars in filamentary clouds, the importance of edge collapse processes. And you'll see 10 minutes there. That's your talk, and then we'll follow.
Okay. Thank you. Hello all. Very good afternoon. I am Naval Kishore Badri. I am a postdoc at Physical Research Laboratory, India. And in this talk, I'll present the results from our recent work, highlighting the role of filaments in massive star formation. The background image you see is an optical image taken from SDSS survey. And this is the monoceros R1 region, which is located at 800 parsecs. These are the reflection nebulae. And in a couple of minutes, I will tell you the story how we have identified a filament, which is in process of collapse and forming the two of these reflection nebulae here. So I'm sure that the audience doesn't need an introduction of star formation and the ISM because all are expert here, but I will highlight that the molecular clouds are basically hierarchical in structures, and it consists the clouds which have larger sizes greater than 10 parsec or so, but the denser structures and the lesser in size, they are known as clumps, and the further most denser structures are cores, which ultimately forms stars due to gravitational collapse. But recent observations, including optical to millimeter wavelength and including Herschel observations, that it has been found that the interstellar medium is full of filamentary features. And these filaments are basically the elongated structures, and they can be seen from the protostellar envelope up to the cloud scale. So these are very ubiquitous structures, and you can see them here in the Eagle Nebula. So in theoretical perspective, people generally consider filaments as a cylindrical cloud, which are in equilibrium between thermal and gravitational pressure. And the stability of these filaments are considered by this line mass parameter, which depends upon the temperature. And the stability parameter is basically the line mass divided by the observed line mass. So if the stability parameter is greater than 1, then the filament is said to be supercritical. And then these filaments are found to be gravitationally collapsed and form these stars. So here I present the two star forming basically complexes. One is the Euclid rift and another one is Polaris flare, showing you the column density variation here. The brightest region are the high column density regions, and even they have the higher stability parameter. Here in the Euclid rift, you see these bright feature actually host the young stellar objects, basically the protostars, but in the Polaris flare, it is devoid of that. So this tells that the filaments are really important, playing a very role in the formation of stars. But to identify filaments in the images, we can visually identify them in the 2D maps, but we really need to identify them as a velocity coherent structures in the position velocity maps. So, I'll not talk about how the filament fragments and into the course, but I will here discuss about one of the important process that is known as the end-dominated collapse. And this is very less discussed in the literature and in the star formation community. So what happens that the filaments, if the filaments is gravitationally unstable and if the gas is allowed to move along the longitudinal direction only, then the filaments collapse to the central region. So in that way, the acceleration of the gas becomes the function of distance, which is measured from center to the edges. And this is the nonlinear equation. In that way, at the edges, the acceleration is higher, and basically the filament is collapsing. So the edge layer will impart higher momentum to the inner layer, and during the course of collapse, the materials gets accumulated at the edges. So this is known as the edge effect. And the observational example is S242 filament. You see the column density map here. At the edges, you see high column density regions. And in fact, one of its edge hosts an H2 region here. And this is the result from the simulation work by Clark et al. Here are two profiles. One is the volume density profile and another one is the velocity profile. So during the collapse, so the volume, you see that the enhancement of volume density at the edges, and in one of its edge, it shows the red shifted motion, and in another edge, it shows the blue shifted motion. That is signifying that the collapse is happening. So here I will just present the result from our work, how we have identified a filamentary cloud, which is experiencing end-dominated collapse in the monoceros R1. These are the integrated intensity maps from 13 CO observations from fusion survey. And in this velocity range, we see this is a molecular cloud complex, and these are the positions of the reflection nebulae. But when we restrict ourselves in the velocity range of -7.8 to 1.3 kilometer per second, you see a nice filamentary cloud. And at the edges, there are two reflection nebulae. That hints that this cloud basically experiences end-dominated collapse, but we need to further confirm this. So what we do, like as we move from one edge to another edge, this is the velocity profile here. And you see some oscillatory pattern, but clear red shifted and blue shifted material. And this is the column density map showing you high column density regions at the central as well. So that is basically the filament is fragmenting simultaneously. But in our recent work, we analyzed the magnetic field orientations in the sites which are experiencing end-dominated collapse. So this image is showing you the Planck 353 gigahertz image overlaid with the magnetic field streamlines, which are basically estimated from the Planck polarization observations. What you see here is that there is a bending of magnetic field at the edges, which are highlighted by these arrows. But it becomes more clear when we basically take the difference of angles with respect to magnetic field and filament spine, and then estimate the distribution. So this shows the linear distribution. And that's this cartoon is showing you that this is the angle is higher and this angle is lower. So as we move from one edge to another edge, the angle should drop as we move from one edge to other edge. So that is the signature that at the edges you see the bent magnetic fields. And so these are the again signatures. We found the similar trend for the four basically nearby end-dominated collapse sites. These are located at less than 2 kiloparsec distances. and that signifies that the magnetic field morphology can be bent due to the accelerated gas motion which is moving to the central region. And that could be another observational proxy, but that need to be confirmed by another observations. Now, I will quickly highlight the another important aspect that people are interested nowadays in the star formation community. Those are the hub filament systems. Here, basically, the multiple filaments are basically playing a role in the formation of dense clump. So for the massive star formation, like it is really required that there should be massive reservoir. And these images are basically, this one is from millimeter observations, and these are some from the infrared. So you see some basically in emission in the millimeter, and then these structures appear darker in the near infrared. So here the interesting part is that multiple filaments basically converges to the common junction, and those common junction are known as hub. And very recent like paper from Kumar et al. They highlight that the most massive stars generally are found to be formed in these hub regions. So we have been following this target. This is the galactic snake infrared dark cloud. This is the Spitzer image, and so we have studied the gas kinematics here. But the interesting part is that this infrared dark cloud consists many hub filament system, and because it appears like snake, so that's called galactic snake. But at the belly of this snake there is a massive source. So these are the sources, and the color shows the mass distribution. So this one is the massive one, and these are the filament skeletons. So we really want to see like the vicinity of this massive source, which basically hosts a massive protostar, which was known from the earlier observations. And then we looked into the archive whether the high resolution data that probe up to like 1000 AU scale is available or not. So fortunately, we found that the JWST and ALMA basically probe this region, this patch of the sky. And from JWST observations, the NIRCam JWST images is present here in the RGB map. But you see that this is the location of massive protostar, and these are the dusty features. So we are saying that whether these structures are basically available at the smaller scale or not. So this structure becomes clear when we take the ratio map of two bands, and the dark feature is showing you the dominance of the pH feature, which is at 3.3 micron. But now in our recent work, we are confirming this, that using the ALMA data, this is the ALMA N2H plus emission in the color map, and overlaid contours are basically JWST ratio map. So this is showing you the significant similarity between these two, and hence we are saying that this is the genuine hub filament structure, but seen at the smaller scale. So from here, we are just confirming that these hub filament structures are not only structures seen at the larger scale, but at the smaller scale as well. And in the summary part, like I will say that end-dominated collapse is the global collapse mode of a filament, which is caused by the self-gravity of filament. But the observational samples are very less, and these samples are basically targeting the cloud scales. But we really need to see more observations at the smaller scale as well. We do see high column density at the edges, and some red shifted and blue shifted motion at the edge. And then curved magnetic field can be another observational proxy. So with that, I thank you all for your contest.
Question back here.
Hi, Juan Soler, INAF. When we analyze the Planck data, one of the reasons why we didn't analyze the orientation with respect to Monoceros R1 is because it's heavily contaminated by foreground and background polarization. So have you done any separation of that background contamination?
No, not this part, but we restrict ourselves to the sites which are less than 2 kiloparsec. So although there are some sites said to be end-dominated collapse site at the larger distance, but yes, only we used the available Planck like polarization data for the nearby sites. So these are just initial observations. So we really need to look into the other like high resolution polarization observation for that. Thank you.
Another question here.
I don't know. I'm actually more from the simulations part, but I'm aware that, like, I don't know if you ever heard the VGT method to detect magnetic field directions from Lazarian and his students. I was, can you, like, since it's the polarization is polluted, is it possible to then use this method and try to, I don't know if you know how to.
I heard about the VGT method, but I'm not like expert on that. Like maybe like our next speaker, like he may tell about later because he is presenting the magnetic field role of magnetic field in the star formation. Yes.
Well, let's thank Neville once again.
Yeah, thank you.
Next speaker, Arup Kumar Mehti, from collision to creation, origin of hub filament systems through cloud-cloud collision.
Hello.
We'll see the
Yeah, hello everyone. I am Arup Kumar Maiti from Physical Research Laboratory. So as you can see, the topic of this presentation is origin of half filament system through cloud-cloud collision. So this is the outline of my talk. So as you know that massive stars, they form within high density regions, and it shows a column density typically greater than 10 to the power 22 per centimeter square. And such high column density regions are commonly found at the junction of filaments, which is known as half filament systems. So recently Naval has talked about this. So this is a famous example of half filament system. Color red presents the hydrogen column density map. You can see several elongated filaments, they are connected toward a common hub. And another process which can also give you high column density regions is cloud-cloud collision. So due to the intermolecular cloud velocity dispersions, it is found that molecular clouds often collide with each other, and it creates a high density region. It creates a high density region at their colliding interface. So this place is also suitable for massive star formation. Now these two theories are mostly studied independent of each other, and in our previous studies of W31 complex and AFGL 5180, we found some interesting results. So as you can see, this is the Herschel column density map of W31 complex, and this is Herschel 160 micrometer image of this source. Now over that we have overlaid the filamentary skeletons obtained from the Herschel data in color white and red here. So you can see several elongated features, they are connecting toward some common central regions, which reflects that in these regions are actually sites of half filament system. And while studying the molecular gas kinematics toward these regions, we detected two velocity components, and they are connected in the position velocity space, as you can see in these plots. So this is known as bridge feature, and these independent velocity components like red shifted and the blue shifted component, they gives you complementary distribution in the plane of sky. So these are actually signatures of cloud-cloud collision. So as you can see in these two massive star forming regions, we have simultaneously detected signatures of cloud-cloud collision and half filament system. And there are also 2-3 sources where people have found this type of signatures simultaneously. Now this raises some basic questions like can a cloud-cloud collision lead to formation of half filament systems, and if so, then how do filaments converge to form such complex morphologies? Now to understand that, we are utilizing numerical simulation data from Ino et al. 2018. So this is a simple model. As you can see, it is a cubical domain having a length of 6 parsec in each direction, and a turbulent and spherical cloud of 1.5 parsec radius that is colliding with a sea of dense gas with a velocity of around 10 kilometer per second, and a magnetic field perpendicular to the direction of collision has been set with a strength of 20 microgauss. You can see at the right side, this is the density and the z component of velocity profile along the z direction. Now for this initial setup, isothermal MHD equations are solved with the presence of gravity, and data were recorded up to 0.7 million year with an interval of 0.1 million year. And you can see here the resulting column density maps in the YZ and the XY plane from 0.1 to 0.7 million year. So the XY plane that shows the development of the compressed layer, while the XY plane showing you the structural components within that compressed layer. Now the simulation introduces sink particles if the density of a certain region goes above some threshold, and if it is a gravitationally collapsing object. So at 0.7 million here, these two arrows are presenting toward two massive sink particles which are observed at 0.7 million year. Now to have a better look in the compressed layer, we have integrated in a narrow range. Now you can see the conical structures of this compressed layer, and these layers have been divided into thin conical cells, and as you can see here, and we have calculated the average density and the z component of velocity profile. As you can see, the width and the density of the compressed layer that actually increases with time, and the entire high density region that comes at an intermediate velocity, which leads to the bridge feature which I was talking in the introductory slides of cloud-cloud collision. Now, if we see the distribution of the magnetic field strength at 0.4 million year, you can see that the strength of the magnetic field, it was initially around 20 microgauss. Now it has been amplified in the order of milligauss due to the collision process. Now, as the width and the density both increases within the compressed layer, so that means that the fraction of the high density gas that is increasing, and high density gas is always susceptible to the formation of pores and filaments. Now, in order to identify those pores and filaments, we have utilized GetaShape over the XY projected column density maps. So the resulting filament skeletons have been overlaid on the column density maps, as you can see from 0.2 to 0.7 million year. And the high density filaments, they are in particular marked in color green, and this circle presents the position of the cores. Now this blue circle having a white edge, that is the heaviest core at that time. So now in this table we have listed the mass of this heaviest core. As you can see, mass of the heaviest core that actually increases with time, and it becomes around 15 solar mass at 0.7 million year. So as you can see, at 0.7 million year, we have a massive core and two massive sink particles in this central region where several elongated filaments are connected. So we can say that yes, a cloud-cloud collision process can lead to formation of half filament system. Now, if we look at the process of filament formation, so the general understanding is that the turbulence within the molecular cloud that initially creates the inhomogeneous density structures within the molecular cloud. Now, as it collides with another cloud due to the shock compression or the oblique shock effect, it gets compressed and form filaments. Now, this compression will be efficient along the magnetic field line. So, the filaments which are perpendicular to the initial magnetic field direction, they will be denser filaments very quickly. So that thing we can also see in this table. You can see this is a ratio of total projected length of the high density filaments perpendicular to the initial magnetic field to parallel to the initial magnetic field. So you can see that quickly the filaments which are perpendicular to the magnetic field, they become denser. So we get a ratio greater than 1 here, but the filaments which are parallel to the magnetic field, they also comes into the regime slowly. So after that, there is a drop in this ratio, but those filaments which are parallel to the initial magnetic field, they actually unstable and diffuse with time. So you can see the drop in the total mass of the high density filaments and length of the filaments. So that is why we are left with only the filaments which are perpendicular to the initial magnetic field. So these slides tells that there is a immense importance of turbulence and magnetic field in the formation of filaments. Yeah. So now once we have the filaments, now the question is how do those filaments convert? So to understand that, we have shown here the mass weighted average velocity and the gravitational field vectors for 0.3 and 0.7 million year. Now these black arrows are on the filament skeletons, and these white arrows are in the surrounding regions. Now in the right side, this shows the relative orientation between the velocity and the gravitational field vectors. So as you can see, at initial stages at 0.3 million year, the velocity vector that is not that is randomly oriented with respect to the gravitational field vector, but at 0.7 million year you can see that velocity vector that is aligned with the gravitational field vector, indicating that at the later stages gravity has a very good effect on the system's evolution, and the filaments are pulled together and form half filament system by the gravity at the later stages. So if I combine everything in a single slide, that yes, cloud collision can lead to formation of half filament system, and it is a combined effect of turbulence which gives you the initial inhomogeneous structures, and effect of collision and magnetic field, they helps to form the filaments and their orientation, and finally the gravity that pulls those structures to form a complex morphology of the half filament system. So yeah, thank you for your kind attention.
Very interesting, very nice simulation. Questions? So maybe to start, would you suggest that the timing has to be somewhat coordinated so that the collapse time in the compressed cloud has to be comparable to the shock passing time or the crushing time? Because if the cloud comes too fast, it might shatter it. If it goes too slow, it's not going to compress much. So is this a constraint, perhaps?
Like in the, you are asking about the maximum velocity of collision?
That's one way to say it.
Like in observed, there is such events like having a velocity of 30 kilometers per second. Also.
And what happened? Oh, you do see the same thing?
Mm-hmm. There is observed site with 30 kilometers per second collision velocity.
Observed. Yeah, I see. Okay. Any question? Would you estimate also that during this quick time of compression, you might get molecule formation also? Or do you need the molecules to be there already?
No, these are actually starting with the molecular clouds. So we are not observing the whether it can create the molecules or not.
So this would not be the same if it's an atomic cloud?
Maybe.
Okay. Yeah. Still have a minute. Well, thank you very much. Very impressive. Thank you. Next talk by Jadhav Omkar. I see you're all friends here sitting together. Role of magnetic fields in star formation. New insights into the galactic snake. And watch.
So good afternoon, everyone. So in today's talk, I'll be talking about role of magnetic fields in the star formation, especially towards a target, Snake Nebula, or galactic snake IRDC G11.11 - 0.12. The outline of my talk will be, I will first tell you about the magnetic field orientations toward the galactic snake and measurement of magnetic field strength through the DCF method. We have also found out some interesting gas kinematics towards our target, followed by some JWST and NRCam measurements towards the galactic snake. So to start with, so star formation is a really complicated process, and it is a interplay between gravity, turbulence, magnetic fields, and stellar feedback. And out of this, gravity is the major driving force which is responsible for star formation. Out of these four, so magnetic fields are the least understood. So if you want to understand the role of magnetic fields, I have selected a target. So what kind of target it is? So it is basically an infrared dark cloud. So as the name suggests, if you observe these clouds in the infrared part, so it's the Spitzer RGB, these clouds appear as a dark feature. So that's why we refer to infrared dark clouds. And these infrared dark clouds are excellent sites for star formation due to their low temperature density and extremely high mass. So these high density features actually appear as a dark feature if you observed in a near infrared or far infrared images. My target is also an infrared dark cloud.
which we call it it's a galactic snake. Why we have selected this target? First of all, it is the first site to consist of multiple hub filament systems, which was reported in the paper Devangan et al. 2024. Also, it does not host any extended S2 region, so there is not significant feedback from the massive stars, so which really helps us to understand the early stages of massive star formation. Also, we have there are two methanol measures towards this target, P1 and P6, which I'll be talking about in the next few slides. So just to give you an overview of the data sets I have used, I've used SOFIA Hawk plus 214 micron data to study the magnetic field orientations, and I've used JWST NRCam data of 3.56 micron, 4.4 and 2 micron to study the near infrared part. So this is the magnetic field structure towards the snake. The SOFIA polarization data, or in general any polarization data, gives you I, Q, U, V vectors, and you can actually easily infer the magnetic field orientation angle and degree of polarization. We have also inferred the magnetic field orientations toward the galactic snake. The background image is the SOFIA 214 micron data emission, and overlaid are the magnetic field orientations. Here the length is actually proportional to the degree of polarization. The two stars actually are the high mass protostellar candidates, which we detected from the 6.7 gigahertz methanol measures. The second image is actually exactly the same, but in this case here the length of the segments is kept constant, and here it is directly proportional to the degree of polarization. What we notice here in these maps here is the magnetic field orientations are perpendicular on the either side of the cloud, and they are somewhat parallel in the central regions. Also, you can see some bend here in the magnetic field orientation. So there are some interesting magnetic field orientations we found towards the cloud, and I will explain it in a couple of minutes that why is this so. But something when we say magnetic field, something really pops up in your mind is like, what is the magnetic field strength value? So I've also estimated that towards the target through Davis Chandrasekhar Fermi method. All you have to do is you need a volume density, velocity dispersion, and polarization dispersion. You can get volume density from the Herschel column density. You just divide it by the width of the filament and you can get the volume density. Here the velocity dispersion, I've used 13CO21 molecular line data, and here we have a polarization dispersion we can get from the SOFIA polarization angle data. You substitute them and perform the pixel by pixel calculations, and you can get the magnetic field strength map. One thing you will notice near the P1, which is the first high mass protostellar candidate, you can higher magnetic field strength values around 600 to 700 microgauss. And near P6, you can find the values are a little bit lower, like 100, 150 microgauss. That is one thing you would notice here. What does that mean? So as I told you earlier, gravity is the major driving force for star formation. If you want to compare which is stronger, gravity or magnetic field, so we use a parameter called as mass to flux ratio, which tells you which is dominant, gravity or magnetic field. So if the mass to flux ratio is greater than 1, you would say that the gravity is dominant, otherwise the magnetic field is dominant. All you have to substitute here is the column density and the total magnetic field strength. As you know, we have only calculated the plane of the sky strength of the magnetic field. So you use this relation that has been come from some simulations from Crutcher, 1.3 times the plane of sky magnetic field strength, you will get a rough estimate so of the total magnetic field strength, and you can get the magnetic field strength, the mass to flux ratio map. You can see if it's less than 1, the magnetic field is dominant. You can see towards P1, it is slightly on the lower side, which shows that magnetic field strength is highly dominating here. And you can see closer to P6, it is supercritical, which means gravity is more dominant. So which are we drawing a two conclusions we are drawing that P6 is more evolved than P1. That could be one conclusion. And also there is another reason that we will draw that P6 is actually in the center of the hub filament system that is detected towards that region. So in the center of the hub, the plane of the sky strength of magnetic field is underestimated. So that is why that could be the reason that the P6 is actually supercritical. So this is things we can draw from the conclusion of the magnetic field strength. Another interesting thing which we investigated from this analysis from the gas kinematics is we observe large scale velocity oscillation throughout the filament. So that is something which we not observe very easily. You can see the oscillations are clearly visible, but you can see in ammonia, you can clearly see the oscillations. So what these oscillations actually signify? So also, if you just break this oscillation into a couple of velocity gradients. You can treat it this a single velocity gradient, this one as single, this one single, and this one single. Break them into a series of oscillations, sorry, series of velocity gradients, and you can actually say that if the matter is accreting in this fashion, like the arrows are indicating, and there is a central star which is forming in the center, that could give rise to oscillations. So material is moving this way, and the star is actually forming in the center. So that could be a reason that the large scale velocity oscillations are present in this filament. Surprisingly, the P1 high mass protostellar candidate which was found was actually here in the center, where there is in the center of the velocity gradient. So that could explain the large scale velocity oscillations that were found towards the Snake Nebula. Now coming to the near infrared part of the galactic snake, this is a JHK band RGB image from VVV survey. You can see the snake appear as a dark feature, and GWST actually data was available towards these cutouts, P1 and P6, I will call them, and I will present you the JWST images towards this target. So towards P1 and P6. First, let's look towards P1. This is the same image of from the VVV survey, and the second one shows the JWST image from the NIRCam. The 4.4 micron is red, 3.56 micron is green, and the 2 micron is blue. So we found some interesting star formation activities towards these small boxes that I have highlighted here. Let me show you in more detail. You can see here. This is an RGB map of the same JWST band. Here the only difference is I want to highlight the extended features which were present in the 4.4 micron wideband. So that's why I put them as red, and the blue and green are 3.56 microns. You can see some jet-like features here present towards here, probably due to the 4.69 micron H2 emission that is present in that band. Yeah, that is, we have found some extended features as well in the 4.4 micron emission in all of the images, if you can see clearly. Also, the P1 high mass protostar candidates, which were found, this is showing some extended emission in this part. So this is exactly in the JWST, they were able to probe the vicinity of this P1 high mass protostellar candidate. Actually, we have also seen some similar thing in the P6 region as well. So Tuart also found some outflow activities and in the 4.4 micron band from JWST. And you can observe similar features in here. You can see the proper these jet-like features that are arising from the young stars here as well. Also some extended emission. One thing that the P6 protostar, which actually having the vicinity, you can observe some circumstellar material in the around the high mass protostar as well. So that is actually not known. We actually discovered it, but there is no explanation like why, what is the reason behind this circumstellar material which we are observing around the P6 high mass protostar. Then finally, I would like to cover the half filament aspect that we found towards these two high mass protostar candidates. You can see that's dark features that are converging towards the center. That is seen in the JWST images as well. And also Naval covered this part as well for the ratio map. You can clearly see the half filament system, which is observed in the JWST images. So it's a small scale half filament system, while this is also, you can see large dark features that are converging towards this center. So summarizing my talk, we have inferred the magnetic field orientations and magnetic field strength, and we determined the magnetical criticality of the P1 and P6, and we also showed that the kinematics towards the galactic snake shows large scale velocity oscillations, and also JWST images towards these snake nebula shows outflow activities and some close-in environment of the high mass protostellar candidates. So that's now I end my talk. So thank you very much.
Very interesting. Very interesting. Over here.
Thanks for your talk.
Yeah.
I'm very puzzled about your mass to flux ratio map.
Yes.
Because so Davis-Shansaker for me has three terms: has a density, has a velocity. So there you have the resolution of the observations, and then you have the polarization dispersion.
Yeah.
And for that you need kind of an aperture, and in each aperture you need to have enough polarization vectors such that the polarization dispersion that you get is enough sample. So how many vectors do you have per unit of resolution in that mass to flux ratio?
Sorry, I could not follow your question. Can you repeat, please?
So you made a map of mass to flux ratio.
Yes.
But the Sophia observations just have like probably 2 beams across.
Yes.
So how do you get more polarization vectors to make a map of mass to
We
flux
convolve.
ratio?
I have a polarization dispersion which has angles. I convolve them with the same resolution as the molecular line data because we use 3 data here: column density, the Sophia polarization data, and the molecular line data. Out of these 3, the poorest resolution has the molecular line data is the poorest resolution, around 30 arc seconds. So I convert them to the.
How many polarization angles do you have per unit of resolution?
Okay. Oh, so around 23 arc second for each polarization vector. Yes, we have binned the data, so you could easily observe the magnetic field orientations. Yes.
Very quick. Yeah, thanks. I love the plots. Every time I try to visualize the magnetic field around like high intensity regions of molecular clouds, I see the vectors shrinking when they get closer, which tells me that the magnetic field is curved. I don't think it's like lower magnetic field strength. It's more like curved. Can you comment on that, or did you look at that?
The curved magnetic field.
Yeah.
That since we are only able to probe the plane of the sky magnetic field, and we don't have like proper plane of the sky velocity motions, but that could be due to the plane of the velocity field. Also, that like the velocity field vectors that are actually bending the magnetic field could be a possibility, because from the sideways velocity motion, maybe that is a reason that could bend the magnetic field, because that could be a reason too.
Thank you again.
Thank you.
Next is Hannah Bish. Talk about LightCube, a 3D model of the local UV interstellar radiation.
Hi, everyone. I'm Hannah Bish. I'm a postdoc at the Space Telescope Science Institute, and I want to tell you about this data product I've been building called LightCube, which is a 3D representation of the local UV interstellar radiation field. And so just so we're all starting on the same page, the interstellar radiation field, or ISRF, is the electromagnetic radiation field produced by stars and interstellar matter that permeates interstellar space. So it's made up of all these photons that are flying around the ISM. And it's important to understand the ISRF because it's responsible for setting the properties of diffuse matter. So the chemical, physical, thermal properties of gas and dust in the ISM are largely set by the ISRF. And it's composed of a blend of components from different sources, as you can see here. But the most crucial to model is the UV regime. And that's because not only is there a very high energy density of photons in the UV, but these UV photons are primarily responsible for photoionizing the gas and for heating the ISM. In addition, the UV emission is really driven by young massive stars, which are very spatially clustered. And so there's a lot of spatial variation in the UV ISRF. And that means that we can't easily model it with some simple, smooth form. And then to add another layer of complexity on there, UV photons are preferentially scattered off of dust grains. So we also need to understand what's going on with the dust to know about the UV ISRF. And so you can see this here on the left is a UV map from GALEX, and you can see this diffuse UV emission there. On the right is an H1 map from GALFA, and you can see that the diffuse UV radiation roughly matches up with the location of these neutral clouds. This particular cloud was our poster cloud for the proposal, so our collaboration refers to it as the ISM shark. We're all very fond of this cloud. Okay, so how is LightCube going to be better than what we have already? So the most widely used models currently are generally from the 60s, 70s, and 80s, and they all assume a smooth, static ISRF. And there have been, a few improvements, a few advances in astronomy in the last half century. One of which is Gaia. And as we all know, Gaia has been an absolute revolution for stellar astrometry. And so we now have precise locations for UV bright stars and therefore the sources of this UV radiation. In the last few years, we've also had a lot of advances in the quality of detailed 3D dust maps. And so we also know the location of these dust clouds that are going to scatter and absorb the UV light. And so we can take our star catalog with precise locations and UV fluxes, and we can take a 3D dust map and put this information into a radiative transfer code that's going to trace the photons as they come out of the stars and move through the volume and are scattered and absorbed. And then what we're left with is what we call LightCube, this 3D model of the UV interstellar radiation field. So I'm just going to briefly talk about each of these steps. So the first component is the stars. And in addition to the precise locations from Gaia, we needed UV fluxes for these stars. And so we turned to a 1978 survey conducted by the TD1 satellite that covers over 31,000 sources and 4 UV bands. If you're wondering why we're using a survey from 1978, that is because it is still the most recent all-sky survey of UV bright sources. And I actually had a chance to talk to some old-timer UV astronomers who remember this survey, and they told me that the data were processed using batches of punch cards fed into a mainframe, which I thought was fun. But it gets the job done. And then the next component is the dust. And so, as I mentioned, in the last few years, there have been a lot of advancements in the quality of the dust maps available to us. So these left two panels were both dust maps that were published in 2019. The right-hand panel is a dust map from just a year later. It has 10 times the resolution. This is the dust map that I was using when I started working on this project. And since then, an even more recent dust map has come out, which covers a much larger volume with about the same resolution. So these dust maps are continuing to improve. And then finally, we combine the stars and the dust using a radiative transfer model called DIRTY that was written by my collaborator, Carl Gordon. And so we take the locations and properties of the stars and dust, and then this radiative transfer model traces the photons as they move through the cube. And this step has been by far the most challenging, a lot more challenging than we originally anticipated, because this radiative transfer is just so computationally expensive. So I've spent a lot of my time on this project trying to work out ways that we can be more efficient with how we're using the code, so that we can build this product with the resources, the computational resources that are available to us. Okay, so now I want to show you a movie of the partial test cube that I've built so far. So this is a slice parallel to the plane of the disk of the Milky Way. The sun is at the center, galactic centers to the right, and then the movie is just going to move up through the disk from below to above the disk. And you can see that these regions of really bright star formation can dominate the ISRF out to hundreds of parsecs. The midplane has a lot of variation. And then as soon as you get to like 150 parsecs above the disk, things smooth out very quickly. You can also make out some shadows where light from stars has encountered the dust clouds, which I think is kind of cool. So I will leave this up at the end of my talk so you can watch it again if you like. But once we have LightCube, we can look cell by cell in these 1 parsec resolution cells to see how the ISRF correlates with other properties. So here you can see that the UV energy density spans over 3 orders of magnitude, which really underscores the fact that, assuming a smooth distribution isn't really a good reflection of reality. And we can look over here at the highest dust density region, which corresponds to where the molecular clouds are. And you can see, there's less variation there, but it's still an order of magnitude. And so, you might expect that inside clouds, the radiation field would be very similar cloud to cloud, but that doesn't appear to be true. So LightCube is going to be a good probe of the conditions in molecular clouds. And that's just one of many, many applications of LightCube. I don't expect you to read all this, but this is an incomplete list of the types of projects I've talked with people about what they want to use LightCube for, everything from planet formation to magnetic fields, to dust properties, the CNM. I'm personally interested in looking at how gas ionization state relates to the radiation field. And so if you think that you might want to use LightCube, I'd love to chat with you because this is a data product that I'm building for the community. And so the needs of the community are really what's driving our decision making and what we're prioritizing as we build this product. And so I will leave out my summary slide and let the movie play, and happy to take questions. Thanks.
Yeah. Very interesting. Let's start. Very interesting, but for dust, those parameters are degenerate. How are you disentangling them, or how do you hope to disentangle them?
Which parameters do you mean?
The dust density, albedo, and scattering are all, you can't just get one out from. So how are you trying to disentangle that degeneracy?
Yes, so at the moment, we are having to assume the albedo and the scattering angle to build this cube. But one of the things that we could potentially do is vary these things and build cubes with different values for these parameters and see how that changes the result. So that's definitely something we could look into more in the future. Yes, and that's also, we're working on the UV first, but we could do other wavelengths as well. They get a little bit more complicated, but that's definitely something we could do in the future too. Thanks.
Yeah. Thanks, really nice work. I was wondering for your sample, because in radiative transfer models of galaxies, we see that emission from one part of the galaxy can heavily affect a different one. So I was wondering for your sample range, how do you take that into account at all?
Yes, so we do have like a general background radiation level that we put into the cube. And then also the final cube that we make is a bit smaller than the dust cube that we have, so that we can account for the radiation that's coming into the cube from outside. And so we've tried to look at how far these stars influence the radiation field so that we can take that into account.
Beautiful work. Please keep up. You've not mentioned Lyman alpha, and that can be a very important photo dissociation source. It's complicated because of neutral hydrogen in the interstellar medium, but there's a new data product coming out of the New Horizon satellite, essentially an all-sky survey in Lyman alpha, which I think would be really important to add to what you've been doing.
And what is that called?
It's just coming on the market now.
Okay.
Thank you again.
Thank you.
Okay, your mic is on.
Thank you, Bruce. It's a pleasure to see all you there. And I should say that this is actually my farewell from the lead of the division. I was there serving since 2006, and we should mention the brilliant persons who were also doing well, like John Dyson, who actually invited me to this division. So my job is now to explain you why NGVLA would be a game changer. And your job is to see something which is not there, actually the Rio telescope. This is the site, and there is the webcam image. You can follow how it will be constructed in these weeks, actually. And the next job you have is to imagine not only the ways and methods and modes I suggest, but quite new things, because this is a completely new instrument, so you should have new ideas. So we will have 244 dishes with 18 meters diameter, and there will be also a short baseline array with smaller dishes. They will be operating in a really large frequency range from 1 to 16 gigahertz, and a dense core with a kilometer scale for low surface brightness imaging, and 30 times longer baseline, like the normal VLA we have now, about 1,000 kilometers, and even higher, like continental scale. And you see this plot there, NGVLA will really have much higher resolution than anything else you can imagine today or in the near future. So then, of course, we will have a large collecting area, so we'll get 10 times the sensitivity of the current Karjansky VLA, and also an order of magnitude higher than the ALMA has today. How about timeline? The full operation will be late 2030s, and this is where we are now, the prototype being installed. So what can we do? And for that, we can consult the so-called key science goals with the NGVLA. And going through that, like star formation, planetary formation, evolution and structure of galaxies, pulsars, then supermassive black holes. This is all actually quite according to the scientific objectives of our division. So yes, NGVLA is for us, or for us as well. So let's just see some examples of the many which we might do. What we see here is mimicking observations of disk formation. So this is protostellar disks, and we have models, like on the right-hand side, we have a 5 AU, one Jupiter mass planet at 5 AU from a solar mass star, quite solar-like temperature, bit larger radius. And what we see here is that the model predicts some structures in the disk with the horseshoe shape and others. And at least at the around 40 gigahertz frequency, ALMA is not able to get anything of it, whereas NGVLA will very well resolve this stuff. So why to go to that low frequencies? This is actually the frequency where even with some grain growth of the dust, you would see an optically thin disk. So that's why it's good. On the left-hand side, we have so-called thermal tomography. We can go down to astronomical unit scales to see how the temperature is distributed. We see 3 millimeter images on the left and 1 centimeter on the right from Satoshi Okuzumi. But we can go for better resolution of the chemistry of the disk, as it was shown by Eleonora Bianchi recently. And of course, we can see much better the outflows, where they are originated, how they are looking like, down again to few astronomical unit scales for the nearby. What is nearby for us? Like Taurus. Yeah, we reach that resolution in Taurus, and we can go for subparsec scales for the nearby galaxies in the star-forming regions. How about stars? Well, nice, exciting examples of runaway obese stars moving through the interstellar medium. We have all sorts of shocks. Yeah, we have a bow shock because of this supersonic, highly supersonic stellar wind interacting with the interstellar medium. And then you have a forward shock to the ISM, and you have a reverse shock to the stellar wind. And in this reverse shock, you can accelerate particles really to very high speeds, and it will generate non-thermal radio emission, for example, synchrotron emission. Of course, a nice field for radio observations like this 3 gigahertz continuum image of EB27 bipolar Benaglia. And of course, we can do that again with much better resolution and also in regions more obscured when we use NGVLA. But let's go for main sequence stars. We know there is some dust around them, and how to see the hot exozodiacal dust. Yeah, we can look for that in the 93 gigahertz, about 3 millimeters. And as this plot below shows, for the presently the stars, there is a chance, depending how we estimate the actual flux, there is a chance to get this hot exozodiacal dust already with 8 hours of NGVLA observations, like Thomas Stuber and collaborators showed. So how about galaxies? Now, I was looking for a nice example of the present VLA studies, and yes, indeed, there is now an ongoing really large, or let's say extra large survey in L-band, 1,800 hours. Yeah, that's quite a lot. All configurations of VLA, and this will be the deepest and highest resolution, both in spatial and velocity resolution, for the H1 21 centimeter and continuum in the L-band. The goal is to cover the full area of 6 actively star-forming galaxies in the local group. These are listed here. And one example here is NGC 6822. This is a low metallicity dwarf. And so this is already out, and more to come. What would we gain using NGVLA? Yeah, of course, with a 10 times sensitivity and angular resolution, we can expand such surveys to nearby star-forming galaxy populations. And don't forget the LIRCs, the luminous infrared galaxies and ultraluminous infrared galaxies. They are quite important when they are absolutely distant at high redshifts, but we learn how they behave when we study the local ones. So we can resolve them with studies, getting the dust obscured starburst and more information on the AGN activity, like it was shown with Yingqing Song for NGVLA already. Pulsars. Yeah, we can, of course, do pulsars, first of all, to find them. It's quite important to see where they are, for example, orbiting the galactic center, but it's not always easy to get them. And also there is a highly scattered signal. So the better thing is using 5 gigahertz or over, but then you need an instrument which is also capable of seeing the weak emission there.
1 minute.
Pulsar.
One
Pardon?
minute. One
One?
minute.
Okay, pulsar timing is next, so it's going. So then just flashing up, we can do, of course, 10 degrees region survey in 10 hours. So that's easy to get the electromagnetic counterpart for gravitational wave sources and so on, for better resolution and imaging of jets and rings around supermassive black holes. And at the end, I will come to my favorite or most loved is to see filaments, fibers, and streamers. And that's what we did with Mika Yuval, and we concluded that watching at this filamentary massive cloud in the right-hand side, the true distributions can be very well uncovered with NGVLA using measurements of ammonia and N2H+. So yes, we can do a lot, and this is up to you. Thank you.
Thank you.
Questions? Hi, Victor. Thanks for your talk. This is Juan Soler. So, full disclosure, I'm giving a review on polarization on Monday. So this is not an editorial question. I actually don't know. So what are the plans of the NGVLA for polarization, and how does it compare to what the SKA precursors are doing now?
Well, I am not that good in that, but I think Eric Murphy is sitting in the room, I guess. So he might be able to answer you on this polarization question. Is Eric there? If not, then we can discuss that offline. The question is very good.
Yes, we'll pose it. While we take one more question, could the poster people please come up? There are 11 posters listed. You'll see the order in a minute. Is there another question? So, Victor, will you combine with SKA and make an Earth-size interferometer?
Well, combination with the new generation Event Horizon telescope will be possible because that will go down to 86 gigahertz, not like the present one. And also the global millimeter VLBI will be operating combined with NGVLA. And that would, of course, be of great use. For SKA, I think it's more complementary, but I should check that what we can do with SKA. Probably SKA2 will be the good for the NGVLA.
Thank you once again.
Thank you.
No, oh, here we go. It looks like Langa Moses is first. Langa here. Is this Langa? Talking about large-scale triggered star formation in Milky Way, and you each have about 30 seconds. Here.
Okay, my name is Langam Moses. I'm talking about large-scale triggered star formation in the Milky Way. Here we have two data which we are working on the Meerkat data and the SLIGSM data from the Apex telescope. And you can see in the middle we have one of the images where we have in the background the Milky Way, and we also have the molecular clouds overplotted on it, and we are trying to see at the periphery where we have the molecular clouds trying to collapse, and we are trying to see the fragments. Maybe we can say that the star is taking place, the star formation is taking place. We're also trying to plot the scaling relationship where we trying to look at the size and the mass and the size of the line width to see how we can try to check the shocked and unshocked clouds which are having the star formation. Now, in the conclusion, we've identified 159 molecular clouds which are associated with the Milky Way, H2 regions, and the supernova remnants, and that's about 60% of triggered star formation taking place in the Milky Way. Thank you.
Looks like Stephen is next because the second one from Hajan may not be.
We discuss near-infrared observations in absorption of C2 and CN. The purpose is to study isotopologues to understand nucleosynthesis and chemical processes that alter the isotopes. The excitation provides information about the density and the temperature of the gas. The first panel shows that we see absorption toward a bright luminous star in Cygnus up to J equals 32. The next panel in the middle shows our 12C, 13C observations. Most of them are consistent with the 12 to C ratio in the local interstellar medium, but toward 29647, which has the highest signal to noise, is the top panel. We don't see it. And we set a lower limit of a 12 to 13 ratio, not of 70, but of 200. And what's very interesting about that is in the next panel, our value is consistent with C2H seen in the radio toward the cyanopolyon peak less than a parsec away. And so we're going to be able to, in our analyses, combine fractionation studies of diffuse gas and molecular gas seen in a diffuse cloud and the molecular cloud.
There is not a poster, but Jeff Linsky would like you to look at poster number 30 when we're at the next session. So this comes, Minia.
Thank you. So both AGB stars represents a very fast stellar evolution phase. And so we have a rather small number of known stars in this phase in our galaxy. And even more, they are quite often confused with other stars like young stars or supergiant stars. So what we did was to use Gaia astrometry to compute very accurate luminosities for these stars from a literature sample, big sample taken from literature, and disclose real post-AGB stars from other types of stars. And we use information about temperature and reddening to calculate masses and also ages and compare those findings with the theoretical expectations. And well, this has been published in Astronomy and Astrophysics. And well, the reference is there. And we also disclose post-AGB stars belonging to the disk to those in the halo. And this is also interesting. So that's it. Thank you.
Thank you, Minia.
Hi, I'm Luli from Shanghai Astronomical Observatory. I study the open clusters in the Milky Way. We all know that in the Gaia era, we found lots of open clusters candidates in the Gaia's data that we found them in the velocity space and to identify them in the calorimetry diagram. So we we have a method that can identify the open cluster detailedly, quantitatively, and that basically is two probability. We compare two probability. The first is the few stars with clusters inside, and the probability of the pure few stars. And we found that in that two histogram, we found that the real open cluster separated largely from the mock few stars, randomly mocked few stars. So this identification method using the Bayesian evidence is really useful for the open cluster identification. Thank you.
Thank you.
Thank you. So hi everyone, I'm András Jó, second year PhD student at the University, Ötvös University in Hungary, and I brought you a poster about my study of pre- and protostellar cores in molecular clouds throughout the galaxy, for which I'm using Planck compact sources as targets. I will present this poster on Monday at 10 o'clock. And if you're interested in the topics of filaments, cores, please do come up to me and have a talk. Write me a message in Slack or anything else. Thank you very much.
Thank you, Andreas. Aurora?
Hi, I'm Aurora Duran. I'm presenting the analytical model of the L1551 IRS outflow. So this is to explain this model and the outflow morphology of some dynamical features of this star, which is a binary. And this model gives us a data cube that can be compared with the observations and finally see the contribution from the binary interaction. Thank you.
Hello. If you saw Lucia's talk this morning, I also work on modeling cosmic rays in the Tiger simulations of the multi-phase ISM. And the one sentence punchline of the poster is that we're able to reproduce the observed cosmic ray electron spectrum in these simulations, which are useful for producing mock synchrotron observations, which can be compared to future observations. So with that.
Thank you, Nora. I think that's the end. So let's thank all of our speakers again. And I hope to see you downstairs now at the poster session where you could talk with these researchers.